Okay, everybody, can you hear me?
Yes, but there's somebody talking in the background.
All right, okay. Well, good morning or good afternoon, maybe good evening to somebody, I don't know. Welcome and thanks a lot for attending the 5th IBS-IFT and MultiDark joint workshop. This year, I mean, we are in somewhat different situation. This meeting is different from the previous ones. First of all, because of the reason that everybody knows well, we could not have, in-person meeting, but only this remote online meeting. Another difference is a nice one that in the previous meetings, the main theme was the dark matter physics and the related particle physics and astrophysics and also the cosmology. But this year it could expand the scope so that the subject now include the another area, the string phenomenology, which becomes possible that you could hire this year, IBS-CTPU, hire 2 new faculties, and Sung Lee, who is one of the organizers, and also Pablo Sola, and who is a very passionate member of the group because he arrived yesterday, as far as I know, and I hope he's attending.
He's there.
In the 2 weeks of.
Hey everyone, yeah, I'm here.
Hi,
I just
Pablo. Welcome.
Thank you very much.
Okay. Well, this is a really nice development, and I hope that with this new development, we could have, you could strengthen the cooperation between the IBS, CTPU, and IFT. Well, anyway, thank you again, and I wish that all of you joined excellent talks and nice discussion. Like what we did in the previous meetings. Thank you very much. And now I will pass the microphone to Luis. Hello, Luis?
Here I am. Thank you, Yvonne. So, as you know, I am the director of IFT. Of course, we are very sorry that this workshop this time does not take place physically here in Madrid or elsewhere. And we hope that soon we will come back to meet in person, something which cannot be replaced by any Zoom or any other platform. In spite of the circumstances, IFT has continued its research and outreach activities at full steam, maintaining all of our different journal clubs and seminar series. This conference has a twofold character, involving both the dark universe on one side and the Swampland on the other. Although both topics look quite different, there are a number of possible connections between both. The Swampland program, as you know, tries to characterize which set of field theories may be coupled in a consistent manner to quantum gravity. The program is also twofold in this purpose. On one hand, there is a more theoretical endeavor, which is to better understand the fundamental principles of quantum gravity. On the other hand, an important aim is also to study whether the Swampland conditions have implications to the observed world. And there are already important hints that that is the case. And for example, Swampland ideas have implications on the nature of dark energy and cosmology in general, and also may have implications in constraints in particle physics, like in axion physics or neutrino masses. And hopefully there is much more to come. So it makes perfect sense to the combination of both dark universe and Swampland physics as in this workshop. So, okay, we all expect that a meeting like this may be useful for both areas and both institutions. And we are sure that the new ideas will appear and collaborations may result from this effort. By the way, we also hope that the COVID virus will be sent soon to the Swampland of viruses, if such a thing exists and never comes back. So, okay, thank you and enjoy the talks.
Okay, good morning. As the chair of the first session, I would like to pass the word to our first speaker. Evan, are you already able to share your screen?
Shall I share the screen? Yeah.
Yes, please.
Oh, it says host disabled participant screen sharing. So whoever the host is needs to let me do it. I think. Should I try again? Or
Changsa, could you try?
yeah, it said host disabled participant screen sharing.
Changsa,
So,
could you try enable?
let me know when I should try again. Ah, now I can do it. Okay. So,
Very good. So we are very happy to welcome Eran Palti as the first speaker from Ben Gurion, and he will enlighten us on fermions and the Swampland. Eran, please.
So hello, everybody. So let me first of all thank the organizers for the invitation to speak. It's a great pleasure and an honor. The title of my talk is Fermions and the Swampland, and it's based on a paper that I wrote earlier this year. Okay, so let me begin. Okay, so the Swampland is defined as all the apparently consistent effective theories that nonetheless cannot be completed to quantum gravity in the ultraviolet. So the picture one can have in mind is the following. We think of some abstract theory space, and at very high energies, we have a quantum gravity, or if you like, string theory, and this is a very constrained theory, so it's a point in theory space. But by the time we flow down to low energies, this single theory gives rise to a huge range of low energy effective theories. And the idea here is that the single theory has a lot of solutions, so many different vacua. And about each of these vacua, we can write down different low energy effective theory. And so the huge number of vacua of the single UV theory, the landscape, let's say, gives rise to a huge number of possible low energy effective theories. However, nonetheless, this huge range of possible low energy effective theories is still only a subset of all the possible low energy effective theories we can imagine writing down. And so in this picture, this kind of big oval is the whole, all the possible low energy effective theories we can write down. The landscape is some subset of it, and then the complement of it is the swampland. So the swampland are the effective theories that have no UV completion to quantum gravity. And this is a very sharp abstract definition, but of course, it's kind of useless unless we can really understand what are the conditions that differentiate a theory in the landscape from one in the swampland. And determining what these conditions are in the effective theories is what the kind of swampland research program is about. So let me begin with the kind of prototypical example of a swampland condition. So this is the condition for an effective theory to have a UV completion. It's conjectured to be such a condition. This is called the weak gravity conjecture. It says that if you have a theory with gravity and U1 gauge field with gauge coupling G, then you need to supplement this theory with a charged particle. And this charged particle must be such that its mass is smaller than its charge. So GQ and Planck Q is the integer charge, if you like, of the particle should be bigger than its mass. And this is a so-called electric weak gravity conjecture. And the magnetic weak gravity conjecture makes a slightly stronger statement. It says, in fact, you need to supplement this theory not just by one charged particle, but by an infinite tower of charged particles. And the mass scale of this tower of charged particle is set by the value of the gauge coupling in Planck units. So what do we mean by an infinite tower of charged particles? We mean there's a tower of particles whose the first one is the mass m infinity, what I call m infinity. The second one is 2m infinity, 3m infinity, and so on. Now, of course, it doesn't really make sense to say this is an infinite tower. It doesn't go into the infinite UV. At some point, at M Planck, the effective theory completely doesn't make sense. But it's infinite in the following sense. If you send the gauge coupling to 0, then m infinity goes to 0, and then you have an infinite number of states within a finite mass range. Okay, so it's a tower such that when you send the gauge coupling to 0, you get more and more of these states. So this is the weak gravity conjecture. I think as Louis mentioned in the introduction, it's quite interesting in the sense of this workshop, because it tells you that if you have a theory with something, so let's say in this case, a theory with a U1 gauge field, you have to add other things. You have to add additional sectors to the theory. So in that sense, it's interesting. There's another proposed conjecture for a Swampland consistency constraint called the distance conjecture. And now it says, well, now let's consider not a gauge field, but a scalar field. We couple it to gravity. And now the statement is that there should be, again, this theory must be supplemented by an infinite tower of states with a mass scale m infinity, such that now this mass scale depends on the expectation value of the scalar field. In fact, it's exponentially small in this expectation value in Planck units. Now, the statement is that this should hold at least for phi bigger than m Planck. So if you give large expectation value to the scalar field, then this exponential kicks in, and this behavior should occur. So alpha is some order 1 coefficient. And both of these conjectures have been tested a lot in string theory, and they seem to be true. Are there any questions about these two conjectures in particular?
Yes,
feel free to interrupt me. Yes?
So if there is a charged particle, this charge must satisfy the weak gravity conjecture, but can we also consider the free U1 theory without charged particles?
So the conjecture, well, okay, so let me explain a little bit. If you look at the conjecture, it says that there should be a charged particle with a mass less than GQM Planck. So this is a mass, this is an energy scale, GM Planck. So below this energy scale, you can have a free U1 theory. Okay, so you can have a free U1 theory, but the conjecture says that you cannot have a free U1 theory valid above the energy scale GM Planck. Okay, so at low energies, you can have a U1 theory, but not above GM Planck. By the time you reach that mass scale, you have to introduce new particles to the theory. And if you send G to 0, this mass scale becomes lower and lower. So you get less and less, the cutoff of a free U1 theory goes to 0 as G goes to 0. Does that answer your question? Or?
Yes, thank you.
Any more questions? Or? Okay, so the distance conjecture is the statement here. I put it here in the corner, but we can kind of rewrite it in an interesting way. We can say that it says that if you have a scalar field, then there must be an infinite tower of states whose mass scale is set by this parameter mu times m Planck, where mu is a derivative of the mass scale of the tower of states with respect to the scalar field. So that's just telling you that there's exponential behavior. And now the distance conjecture says that this must hold true, at least for a large expectation value of the scalar fields. However, one can consider whether this should be true for any value of the scalar field. And indeed, and indeed, this is what you might call the magnetic scalar weak gravity conjecture, is a statement that this must be true no matter what the value, expectation value of the scalar field. There must be an infinite tower of states that couples, satisfies this property on its mass. The derivative with respect to the scalar field of its mass is this parameter mu, and the mass scale is then mu m Planck, at least for small mu. So this is what it proposes, and this should be independent of the expectation value of phi. So these are actually two independent conditions, and it's important to note that. And this also passes tests in string theory. It's less tested than the distance conjecture. But I think so far it's passed all the tests. So the nice thing about rewriting the conjecture this way is now all of a sudden we see that kind of distance conjecture, if you like, the magnetic scale or weak gravity conjecture, has a similar form to the weak gravity conjecture. They're both telling us there should be an infinite tower of states whose mass scale in Planck units is set by the value of, let's consider the weak gravity conjecture. G is the coupling, the 3-point coupling of the gauge field to 2 of the charged particles in the tower. So it's the tower state. The mass of the tower state is set by the value of the coupling of the field to the tower. Now, mu, it turns out to be also be exactly the same thing. It's the coupling of a scalar field now to this 3-point coupling to the tower of states. And so in this sense, they are kind of on the same footing. They're just telling us if you have a field, a gauge field or a scalar field, there must exist an infinite tower of states. And the mass scale of this tower of states in Planck units is set by the value of the coupling of the field to the tower. So that's what these statements are saying. Are there any questions about this? Okay, so that seems to be what string theory seems to be suggesting. At least all the tests so far seem to be satisfying it. And so we have to try and understand, what does this mean? What is this telling us? This is where we have to interpret this. So it's natural to interpret it in terms of some physical processes. So this is a statement about parameters in a Lagrangian, but we can turn this into, this parameter appears in a physical process, for example, in the exchange force between 2 of these particles. And this is one interpretation, or say the weak gravity conjecture. This leads to the interpretation that gravity should always be the weakest force, for example. So you must have some particle with a mass that's less than its charge, so that there's the weakest force. But this 3-point coupling also appears in a different diagram, and this leads to a second interpretation of what these conditions can mean. Instead, you can think of this one loop diagram, and now it's relating this condition to something about the one loop running of the gauge coupling, the kinetic term for the fields. And it's possible to also just consider this, maybe it's just a statement about the 3-point coupling. I don't know. But these are kind of the more traditional physical explanations. And so I'm going to be concentrating about the second interpretation, that this is trying to tell us something about the behavior of one loop running of couplings in any theory that has a UV quantum gravity completion. So this one loop interpretation can be interpreted as somehow the requirement of some kind of strong coupling unification of all the fields in your theory. It's sometimes called the emergence proposal. And the idea is the following. Let's think about the gauge field case, for example. Then 1 over g squared, we can rewrite the weak gravity conjecture as follows. Is there a question? Oh, no. We can rewrite the weak gravity conjecture as follows. We write 1 over g squared is the same as the sum over charges from n equals 1 to n, some big N. And this then gives us that 1 over g squared goes like n cubed, big N cubed, since this is quadratic. And then we set n cubed to be m infinity over n Planck squared, and then we see that this is just gives us the weak gravity conjecture. So this is just a way to rewrite the weak gravity conjecture that I talked about, the magnetic one. But then how do we interpret these two conditions? Well, the first condition can be understood as related to the one loop running of the gauge coupling, because normally you have a log here, but this is essentially the one loop running of the gauge coupling from a tower of states, the tower of states that we've been talking about. And what is this condition here? Well, if we think about such a tower of states going up to some n, we're taking n states in this tower, then the energy scale at which you, the UV scale of this tower at which you cut off this tower is n times m infinity. And then this statement is just telling us that this UV scale was set to be m Planck over square root of n. That's a very well-known scale. That's a so-called species scale. It's the scale at which gravity becomes strongly coupled. Okay, so that's what these two conditions mean. It's an interesting way to rewrite the weak gravity conjecture, which somehow might be telling us that there's some physics behind this. So in other words, in this interpretation, the weak gravity conjecture is equivalent to fixing the UV boundary conditions to strong coupling for any U1 at a species scale, at this energy scale. So what do we mean by that? We mean that if you look at the UV running of the gauge coupling, the IR value is given by the UV value plus the one loop running, that's this contribution here. And what we're saying, the weak gravity conjecture is just saying that the IR value is essentially dominated by this contribution. That's the same thing as saying that when you reach the UV scale, in this case, the species scale, G is of order 1. Okay, the species scale is a scale at which gravity becomes strongly coupled. Saying G is of order 1 is also saying that the U1 becomes strongly coupled. So it just means that the weak gravity conjecture is somehow telling us that all fields must become strongly coupled at the same scale. It's a kind of unification. A slightly more brave, if you like, interpretation is that at that UV scale, they are not fundamental and they are emergent gauge fields in the IR. So it's this kind of picture. We imagine starting from some, let's say, some Maxwell theory at low energies, and then we just increase the cutoff for that theory. We don't do anything to it. And what the Swampland is telling us, what this is telling us is that you can't just leave pure Maxwell theory until you reach M Planck, and then all of a sudden all the degrees of freedom come in and fix the theory to be a consistent theory of quantum gravity. The theory has to kind of plan ahead, and you have to change the way that it runs. It runs into quantum gravity, and the scale at which this running has to start happening has to happen quite fast. Is this M infinity? That's where all these states are coming in, and they're making the theory strongly coupled. Sufficiently lower scale at the scale M Planck of square root of n. Okay, so that's the interpretation of this one loop running. What this could mean, this evidence, what it can mean more fundamentally. And now the idea of the paper is the following: that while this interpretation of the 3-point coupling is a kind of force diagram, this can never be applied to fermionic fields, only to bosonic fields, because only bosonic fields can have a self-force between particles. You can't exchange a fermion here. On the other hand, this kind of interpretation, the one-loop interpretation, there's no problem with having a fermion here in the external legs. So that means that we should be able to apply this interpretation to fermionic fields, not just bosonic fields. And this is what I studied in this paper, it's what I proposed. So this is a kind of fermionic version of the weak gravity conjecture. And it says that if you have a theory now with a fermion, then you must supplement this theory with a tower of states. And this tower of states, the idea is just to keep in mind the same kind of diagrams. Now we have an external fermion. So in fact, in this tower, now we have to introduce at each level a boson and a fermion. And the coupling of the fermion to the tower, to each level of the tower, goes like the level in the tower times some universal Yukawa coupling. And then the statement is that, again, the mass scale of the tower is set by the value of the coupling of the field to the tower in Planck units. So that is completely analogous to the M infinity is G M Planck for the weak gravity conjecture, or M infinity is mu M Planck for the scalar. For the fermion, M infinity should be Y M Planck, where Y is the Yukawa coupling. That is the proposal. And the logic is the same as what I just explained in the previous slide. It implies that the fermion becomes strongly coupled at the same scale as the other dynamical fields, so at the species scale. Are there any questions about this fermionic version of the weak gravity conjecture?
So do you need these pairs? I mean, this pair for each n, or?
Right. So I'll talk about that in 2 slides from now. So can we just delay the answer to that in a second, and then any other questions? Or okay. So let me just make an important point, though. This is an important point in the following sense. The fermionic coupling has no normalization. So what do I mean by this? It means that in the case of a gauge field, charge quantization implies that somehow G is a universal coupling to all the states. So in other words, if you have a gauge field that couples very weakly to some particle, then that means that that gauge field couples weakly to all particles. So, okay, so let's say you have a gauge field that couples weakly to a particle of charge 1, then it's not going to couple any more strongly to any other type of particle. That's arising because there's charge quantization, and this is normalized. So in other words, if you have an IR theory, we have a gauge field that's very weakly coupled to some charged particle, then the weak gravity conjecture tells you you must have a light tower of states. Okay, so that's an important constraint on the theory. On the other case, with the case of a scalar field or a fermion, they are not normalized. What do I mean by this? I mean that a scalar or a fermion, at least a generic scalar or fermion, for example, if something has like a gauge transformation, like a gaugino or an axion, that's not true, but a generic scalar or fermion can couple parametrically small to one state in your theory, whilst coupling to other states more strongly. Okay, so you can have like zero, you can have a theory with a scalar field that couples with zero coupling to some state or very small coupling to some state. Still, you don't necessarily need the light tower state. Instead, what the conjectures tell you is that the light tower states, the tower become only light if you couple weakly to the tower. Okay, so it's still true that if you have a scalar field, let's say, or a fermion field, then you cannot have a fermion weakly coupled to everything. The fermion must couple to some particle stronger than gravity. In fact, to an infinite number of particles stronger than gravity. That's the statement of the conjecture. But it's not true that if you have a fermion weakly coupled to something in your theory, you need the light tower state. Okay, in that sense, it's much less predictive and constraining than the gauge one. Okay. Are there any questions about this point or? Okay, so let me get back to this point that Sungju raised, that why am I introducing now two states at each level of the tower? In the other cases, I just had one state. Well, you could theoretically consider, you can induce the one loop running that I'll be talking about with just scalars in the tower by having some universal fermion here in the loop. Of course, the big difference is when you have a fermion, you can't just have a scalar here or a fermion here or something like this. You need a scalar and a fermion. That's the big difference to the case of a boson, the weak gravity conjecture for bosonic fields or for scalar fields. That's why we seem to need to introduce at least two new particles. You could consider a tower of scalars in a single fermion, but this doesn't seem very natural because what is this special fermion? What is its role? In this case, the IR running is not coming purely from the tower. There's some other kind of degrees of freedom. So I think this is very unnatural. It's also possible to show that this could never work if this fermion is charged, because if it's charged and this these have to also be charged, and the charge of these are increasing and this is staying constant, this will not work. So instead you need a tower of charged fermions and charged bosons. And it also would seem quite unnatural in this case. Why should the Yukawa coupling, another question is, why should the Yukawa coupling increase with the level of the tower? Why would this structure arise? Well, all of these things are completely explained. Why we need a fermion and a boson in the tower, why this should increase with n, if we just propose that what this is telling us is that we need supersymmetry at the tower mass scale. So since you need a fermion and a boson to run in this loop, this seems to suggest that by the time you reach the mass scale of this tower of states for a fermion, supersymmetry should be restored. This is not so unnatural. The tower, as I explained, is precisely it's running you towards the unification of quantum gravity. And in the UV, supersymmetry does seem to be a part of quantum gravity. So it's not so crazy. So I think that this would suggest to me anyway, that the fact that you need this partner fermion, boson fermion pairs running in the loop, another conjecture, which is that supersymmetry should be restored by the mass scale of the tower. So in other words, there should be a tower with the Yukawa coupling to it y, and supersymmetry cannot be broken above this scale, so that you get these fermion bosonic pairs which induce this tower running. Are there any questions about this? Or since you asked the question, does this explain? Or
yes, thank you.
Okay, yeah, thank you. So that's the proposal. And of course, if you have supersymmetry by the time you reach the mass scale of the tower, then the fermionic versions of the conjectures just follow from the bosonic ones. So for example, if the fermion is part of a gauge multiplet, then the gaugino-Yukawa coupling is just a gauge coupling. So the fermionic weak gravity conjecture is just a normal gauge, just a normal weak gravity conjecture. If it's sitting in a chiral multiplet, then it's just the scalar coupling. That's the scalar weak gravity conjecture, the magnetic scalar weak gravity conjecture. So they follow from this. If it's a gravitino, it's sitting in a graviton multiplet, so its coupling is non-renormalizable. So a gravitino couples to the supercurrent with 1/m Planck coupling. And if we look at the one loop contribution to its kinetic term running, so this kind of diagrams with n particles, well, they have to go like n, and since coupling is 1/m Planck, they have to go like the cutoff scale of m Planck squared. And since if we take the cutoff scale to be the species scale, that's exactly 1. So that's precisely what the emergence proposal says. In other words, gravitinos become strongly coupled at the same scale as gravity, as you would expect. Another interesting fermion is the Goldstino. And the Goldstino has two types of couplings. There is this kind of coupling that goes like the F term, but there's also, in the presence of gravity, a coupling of the Goldstino to the supercurrent. And then this coupling works exactly the same way as the gravitino. So the Goldstinos also work just fine if you have supersymmetry. They behave like the Gravitinos. They become strongly coupled at the species scale. And that, of course, makes sense because the Goldstino gets eaten by the Gravitino if you break supersymmetry. Now, it is possible to consider a stronger
we have about
version.
2 more minutes.
Yeah, it is possible to consider a stronger version of the conjecture, which is that the supersymmetry breaking scale should be lower, not just in the one set by the fermionic tower, but by all of these towers that occur. So if that would be true, that would be a much stronger statement because if this G is normalized. So that means that if you have a weakly coupled gauge field, you cannot break supersymmetry at too high a scale. It seems a much stronger statement. I don't know if it's true or not. I'm agnostic about it, but I would say that it seems to, even the stronger statement seems to pass the test that I did in string theory, the preliminary tests. So I don't know if this is true or not. This is something I think to be tested in the future. So I mentioned string theory tests. I'll just mention a couple of the tests that I did, very basic ones. So let's consider, so as I said, we want to test whether supersymmetry broken can be broken above the mass scale of this tower of states. If it is broken below it, then we know that the conjecture is satisfied. That's what I said. If there's supersymmetry, the conjecture follows from the bosonic ones. The highest scale at which you can break supersymmetry is the string scale. That's kind of non-supersymmetric string theories. And how do we suppress the Yukawa coupling to the tower of states or to all states? We want to make this Yukawa coupling small. Well, one way to do that is just to send the string coupling to 0. And so what I did was to extract the string coupling dependence of any Yukawa coupling. The way you do that is you write down the effective theory in d dimensions, and you dimensionally complete with the only dimensional scale in the problem, that's the string scale. And then the values of the string coupling in front of the operators is just given by the number of, by the diagram that's used for them. So if you're looking at open string Yukawa couplings, there's p equals 1, that's a disk diagram. If it's a closed string Yukawa coupling, that's p equals 2, that's a sphere diagram. And then when you correctly normalize everything, you find that the normalized Yukawa coupling goes like this power of G string. On the other hand, the string scale goes like this power of G string. And then you can show that indeed the dependence on the string coupling of the Yukawa coupling scale, M infinity Yukawa coupling, is always bigger than the string scale. So this tells you that at least using the string coupling only, you can never make this fermionic tower lower than the string scale. And so indeed, supersymmetry is restored by the mass scale of the tower. Or in other words to say is that if you go to sufficiently weakly coupled settings, this string scale would always be lower than this fermionic tower. So that seems to say that you can't break supersymmetry above it. You can play a similar game with Kaluza-Klein supersymmetry breaking, so Shirk-Schwartz. That's related to flux supersymmetry breaking. You can show that if you make the volume bigger, then again, the KK scale, which is the scale of supersymmetry breaking, is below the mass scale of Yukawa couplings, at least their dependence on purely on the volume. And then one may consider more complicated string scenarios, like large volume scenarios. Again, it seems that supersymmetry breaking always occurs below the scale of the coupling of the fermions in the theory. So to summarize, quantum gravity manifests certain apparently universal constraints to low energy effective theories, not to lie in the swampland. I propose constraints which arise from the presence of fermions in the theory. So again, you must have a tower of states with the mass less than the Yukawa coupling to the fermion. Okay, so that's like the weak gravity conjecture. There must be tower of states that gravity couples to less strongly than the fermion does. So this does not mean though that if you have some fermion with a small Yukawa coupling to some particle in the theory, there's a light tower. That's important. It's less restrictive than the gauge one in that sense. I also propose that supersymmetry should be restored by the tower mass scale, just because when you run things in a loop, you can't just run scalars or bosons. You need a scalar, you can't just run scalars or fermions, you need a scalar and a fermion. So it seems to be telling you these pairs must be coming in. And I also propose a strong version of this, that perhaps the supersymmetry must always be broken below even GM Planck. Preliminary tests in string theory seem to suggest that this could be true, but this is a much stronger version, so I'm not 100% sure, but I think it's something to think about. So thank you.
Thank you very much, Eran.
Yeah.
Are there more questions, please? So while people can type in their questions or prepare to ask, could I first ask again? So in a string compactification, for example, a heterotic string model, or this tower of states would be the tower of massive string excitations, because the tower mass is above the string scale. Did I understand this correctly, or where would I have to search for this tower of states?
Yeah. They may be massive string excitations. They may not be. But if you just have any 3 states in your theory, the string dependence. So what I showed is not necessarily that they're above the string scale. It's just that you cannot use the string coupling to make them lower than the string scale. So that means that there's always some. I don't know if they are string states. They don't have to be string oscillators. But what I argued is that any tower of states that you have, the string coupling dependence on the Yukawa coupling of that tower states will be such that you can make the Yukawa coupling go to 0, as you expect when the string coupling goes to 0, but not faster than the string scale going to 0 in blank units.
I see.
I didn't say what that tower is, and that's just counting from powers of the string coupling in the appropriate sphere or disk diagrams. Yeah, I don't know. I think it would be interesting to study more concretely what the tower is in various settings, and whether it can be made lighter than supersymmetry breaking scale in certain scenarios. If it's above the supersymmetry breaking scale, then the fermionic versions essentially match the bosonic ones. So if there's evidence for the bosonic ones, then the fermionic should also hold.
Thanks.
Yeah.
Are there more questions from the audience?
May I ask another question? Do you have some comment on the applicability of the distance conjecture? I mean, is it applicable to any kind of scalar field, for example, the standard model Higgs field or any other scalar field?
Well, the distance conjecture, I mean, there's kind of various versions of it, but you need at least to have a super Planckian expectation value. Now, if the field is exactly massless, so it's a modulus field, then there's no energy scale associated to the expectation value. So that means you can have a low energy effective theory where you give a field a very large expectation value. So the conjecture has mainly been tested for the case of fields with no potential. Something like the Higgs field has a potential. And that means that if you give it a very large expectation value, then there's a large energy scale, energy density associated to it. And now the question is whether the distance conjecture should also hold for fields with a potential is a more subtle one. I would say this evidence so far seems to suggest the answer is yes. So that means that it should even apply to things like the Higgs field, but it's just been tested less than the case with fields without potentials because, because it's a more complicated setting. But in principle, I would say the answer is yes, it should hold for any field. Of course, the Higgs expectation value is very, very small in Planck units, so it doesn't tell you anything interesting. E to the minus h over m Planck is essentially 1, so it just tells you there's tower of states near the Planck scale. That's not so interesting, but yeah. Does that answer your question?
Yes.
Can I ask a question?
Yes.
Please.
Yeah, since the distance conjecture has to do with the more close relation to do with the existence of moduli or something, does this conjecture have an implication to the current moduli stabilization program? Because it practically uses effective field theory.
Implications for the moduli stabilization program?
Implications to the current moduli stabilization programs in string theory. It just says that if moduli becomes large, one effective description becomes invalid, and the current moduli stabilization program, I understand, uses definite effective descriptions or so on.
Right. Yeah. So the modular stabilization, when it occurs, it doesn't really occur at parametrically large distances in field space. I mean, the minimum of the potentials. Typically, if you want to probe very large distances in field space, those would be runaway regions in the potential. So, and you can apply the distance conjecture to essentially try to argue generally that must always be the case. So if you have any kind of potential for the moduli, it has to be runaway at sufficiently super-Planckian distances in the field space. So in that sense, it has implications for the program because it suggests that you can never have a modular stabilization scenario where the minimum of the potential is at parametrically large distances in field space.
Thank you. Yeah. Thank you very much. Yeah.
That would be an implication for it. Yeah.
Thanks a lot. Yeah.
Sure.
Okay, I think unless there are urgent more questions, it's time to move on. But before, let's thank Eran Palti again for his very nice talk.
Thank you.
And our next speaker will be Max Wiesner.
Morning. I try to share my screen. Here. Share. Can you see my screen?
Yes, very good.
Perfect. Just.
So we welcome Max Wiesner from IFT, and he will talk about quantum corrections for 4D n=1 emergent strings and the weak gravity conjecture. Please, Max.
Thank you, Timo, and good morning, everybody, or good afternoon, wherever you are. And I will talk in this workshop today about the work that is going on with Daniel Klever from Mainz, Timo in Hamburg, and Songju from IBS. So this is really, among other things, an IBS-IFT collaboration that I present here. And so this work will be another puzzle piece in the big Swampland program that Aaron so nicely introduced already before, so I don't have to lose many words on that. I also have a way less sophisticated picture to depict it. So the big idea is that the Swampland program aims to draw a line between those effective field theories that are consistently couplable to gravity, thus belong to the landscape, from those that don't allow for a coupling, consistent coupling to gravity. And the idea is that one tries to find global consistency condition imposed by quantum gravity to draw the lines between these two. So in the past years, there has been like an entire set of Swampland conjectures that try to identify these consistency conjectures, conditions imposed by quantum gravity. I just listed a few. Aaron also already reviewed some, and you can also read it in his review. But here we will focus on the Swampland distance conjecture and the weak gravity conjecture. Let me just briefly review what this is about, focusing just on the aspect, because there's been written a lot of stuff about these two conjectures, just on the aspects that are relevant for this talk. So the Swampland distance conjecture, that says that at infinite distance in moduli space, so once we approach an infinite distance in moduli space, an infinite tower becomes exponentially massless in Planck units, and therefore makes the EFT breakdown close to this infinite distance point. On the other hand, the weak gravity conjecture tells us that for the decay of extremal black holes, we need states in the theory that are self-repulsive, such that the gravitational attraction of a state, self-attraction of a state, m squared over m Planck squared, is smaller than the repulsion due to some gauge theory, which essentially is the statement that the mass should be smaller for these states than its charge. Our goal in this work is to test the Swampland distance conjecture and the weak gravity conjecture in 4D n=1 setups, because there's been a lot of stuff written in 4D n=2, but we now want to look at 4D n=1. And our setup of choice to do this is F theory on Calabi-Yau fourfolds. So what we will look at are infinite distances in the classical Kähler modular space. So we can roughly say we want to look at limits in the Kähler modular space where we blow up some Kähler volume, call it T, to infinity. This has already been investigated in some detail by Songju, Wolfgang, Lerche, and Timo last year, but here we will refine this analysis a little bit. So if we now have a gauge theory that becomes weakly coupled as we approach this infinite distance limit, we know that also what Aaron in his talk previously summarized, the weak gravity conjecture requires states with masses that also go to zero asymptotically. So one may now ask, okay, what are these states in this classical Kähler modular space infinite distance limits? So this can, on the one hand, be a KK tower, of course, because after all, we're going to a large volume limit, and there we would expect that KK modes become massless. But this would yield a partial decompactification, because this KK tower essentially tells us, okay, we decompactify our theory, so we cannot treat it as a 40 n equal 1 quantum gravity theory anymore. The other option could be string states, that if we find a limit where a string becomes massless or tensionless at the fastest rate, one could also look at these string states and see whether these are the ones that satisfy the weak gravity conjecture. The big difference is that the string states are not associated necessarily to a decompactification. And this led in a different paper by Songju, Wolfgang Lerche, and Timo to formulate the emergent string proposal, that if we have that any infinite distance limit, which is not a decompactification, reduces to a weakly coupled string theory, and that the massless excitations that are required by the Swampland distance conjectures are the excitations of this weakly coupled critical string. So, and this is the case, the string states that we will focus on here, because we want to look at states that are infinite distance limits that are genuine for the n equal 1 limits. So let me, before going to the details, summarize my three main messages that I want to convey in this talk. So the first thing that I want to do is to prove that this string, this emergent string in our setup, at an equidimensional infinite distance point is unique, such that there's only one weakly coupled string that becomes tensionless at the fastest rate. Second, we will supplement this classical analysis by including the leading perturbative corrections at order alpha prime in the F theory setup, and show that these corrections are actually needed to ensure consistency of the emergent string limits. And thirdly, to come to the weak gravity conjecture, we show that the weak gravity conjecture is still fulfilled to leading order, including also the perturbative alpha prime corrections, and that we can actually use this to derive constraints in the form of on the alpha prime corrections by using heterotic F theory duality. So these are the three messages, and you will see them throughout the talk now and then. So what is our setup? Our setup is actually an elliptically fibered Calabi-Yau fourfold. So just an elliptic vibration over some B3. So now the Kähler moduli space that we are interested in is just spanned by H11 B3 Kähler moduli that essentially parameterize the Kähler form J. That gives us, among other things, the volume of the B3. So now I said we are interested in limits that are not decompactification limits. So we cannot just take all the Kähler moduli to blow up simultaneously, because this would just give us a decompactification limit. So we have to take a more sophisticated limit. And the intuition here is what it was used by in these papers, is that instead of blowing up all Kähler moduli, we keep the volume constant such that we don't compactify by shrinking one cycle and blowing up a different dual cycle. And this is possible while keeping the volume of the entire B3 constant if we have one Kähler generator whose triple self-intersection vanishes. So this is an important thing. And so if we have one of these Kähler congenerators that has triple intersection, vanishing triple self-intersection, there are two options. So either also all J naught squared is 0, which is called class B, or in the other case, J naught squared is not 0, but G naught cubed is 0. This is what gives us what one can call J class A, and this is the focus here, because they are similar, but there's some slight difference. But to keep the discussion simple here in this talk, I will just focus on this case that J naught squared is not equal to 0. If this is the case, one can write down, and this has been done already in this paper in 2019, one can write down a limit for the Kähler form, essentially blowing up the Kähler parameter associated to J naught and blowing down some other which correspond to the Kähler cone generators with a non-vanishing intersection with J naught squared. In this way, one achieves what I said before, that one blows up one direction and shrinks the other direction while keeping the overall volume constant. And now there is a special curve, which is just J0 squared, which is also important that I made the differentiation up here, which only exists for the J class A element. So let's focus on this curve, J0 squared, which you can easily show using the intersection numbers that it shrinks in the limit lambda to infinity. And now B3, our base, can be shown to be a fibration of two, and there are two possibilities for this fibration. First, B3 can be a P1 fibration. This is the case if the anti-canonical class and C0 have non-vanishing intersection, so K bar C0 is equal to 2. Or B3 is a T2 fibration in which the anti-canonical class and C0 have vanishing intersection. So, and we will see later on that these two possibilities actually lead to quite different physics. So where come now the emergent strings in the game? So let's take, for instance, the first possibility that B3 is a rational fibration. One then takes a B3 brane wrapped on C0. One can look at, for instance, the world volume theory of this effective string and see that this gives rise to an heterotic string, which I call emergent here because it becomes tensionless in the asymptotic limit where we take lambda to infinity. If one now has a gauge theory on some divisor S, which is part of the discriminant divisor, and S dot C0 is not equal to 0, this becomes weakly coupled. So that the gauge coupling, which is essentially the volume of this divisor S, becomes very small. So if one now looks at the string excitation modes of this heterotic string, one can actually see that the excitation modes satisfy the weak gravity conjecture, because essentially using that the gauge coupling and their mass are related, like I wrote up there, and the fact that we can relate the mass of these excitations, and we can look at the charges. One can see that there's always a sublattice of charges that satisfy this condition here, such that the weak gravity conjecture is fulfilled. So one can now wonder, so everything is fine and we can go home or go back to bed. Also, what is the deal of this talk? There are some open problems. So first, can there be multiple strings that become tensionless at the same rate? So this could, for instance, happen if we have a B3, which is just a product of 3 P1s, and we blow down 2 P1s and blow up 1 P1s. We can also keep the volume constant, but we would have two competing tensionless strings. Second, all the analysis that I presented so far, which was essentially a recap of what was done by Liliach and Weigand in 2019, was purely classical. But we know that the any premoduli space is not classically exact. And quantum corrections can obstruct classical infinite distance limits, which we already observed in n equal 2 setups, such as the vector multiplet moduli space of type 2a on Calabi-Yau 3-folds, or the hypermultiplet moduli space of type 2b on Calabi-Yau 3-folds in these papers. And there's another problem, and which is actually the reason why we would expect quantum corrections, is that the shrinking of the fibril curve, which carries the D3 brane that gives rise to heterotic string, can be problematic if the mass, if it shrinks faster than any KK scale, such that the mass of the heterotic string is lower than the KK scale of the theory, because then we would expect a critical 4D string theory because we can decouple the 10D physics completely from the 4D string. And in the analysis of the type 2b hypermultiplet moduli space, we observed already before that the quantum corrections precisely obstruct limits with classical, which would classically be associated with an intrinsically 4D string. And the third problem is, okay, I said on the previous slide that the weak gravity conjecture is classically fulfilled, but what happens now if we include quantum corrections? Does this weak gravity conjecture survive including quantum corrections? So let me directly give you the answers of this to these questions. First, the answer to the first question, which was what happens if we have multiple fibers that become small at the same rate. One can actually show that there's a uniqueness result. That for any J class A or J class B limits, one of the following always has to hold. So either B3 has a unique P1 fibration and the fiber shrinks at the fastest rate. This would give rise to a unique emergent heterotic string. or B3 has a unique T2 vibration and the fiber is the one that shrinks at the fastest rate. This would give rise to an emergent type 2 string, so not a heterotic string, but here we would have a unique emergent type 2 string, or no such unique vibrations exist, but it is always the KK scale that goes that goes to 0 in the asymptotic limit faster than the tension of any solitonic string. So this would always be the decompactification limit. So of course, since we're interested in this emergent string limits, the two first cases are most interesting for the rest of the talk. The second is the question of quantum corrections. How do they affect? So, and here we have to differentiate between the two types of vibrations of B3 that we can have. So first, there are alpha prime corrections to T2 vibrations. One can actually show that alpha prime corrections do not obstruct infinite distance limits with finite volume, which are the limits I'm talking about the entire time. And the classical analysis just goes through, so we don't have to worry about any alpha prime obstructions. The reason essentially is that winding modes along the torus fiber give the leading KK tower upon two T dualities, which we can perform in the case of a T2 vibration. In that case, we just see that the tension of the emergent type 2 string and the KK scale are locked to be order 1, and so we have indeed an emergent string limit. For P1 vibrations, it's a little bit different. There, alpha prime corrections obstruct infinite distance limits with finite volume. So the classical limits that I talked before are obstructed here. And this is because perturbative control is lost at finite distance in the Kähler moduli space. And thus, we cannot talk here about an emergent string limit. One can, however, save the day by slightly rescaling the limit, by giving up that the overall volume of the B3 is constant. And these are marginally allowed by the alpha prime corrections, and indeed give the correct behavior, correct relation between the heterotic string scale and the KK scale, which is order 1. And these are the emergent string limits that survive quantum corrections. Third, the weak gravity conjecture, which only applies to P1 vibration, because here we have a weakly coupled gauge theory, including the alpha prime corrections to the F theory geometry, ensures that the weak gravity conjecture is still fulfilled a leading order in the weak coupling limit. And still there's a sublattice of super extremal states in all cases. So let me give some details on the quantum corrections. So what we look at, as I said, is the 4D effective theory of F theory on the Calabi-Yau fourfold. We have H1,1 chiral multiplets, which are essentially the volumes of devices of this base B3, which have dual linear multiplets, which are essentially the volumes of 2 cycles, and the Kähler potential, which is essentially the volume of B3. Now these people up here, in a series of papers spanning over quite a number of years, have looked at higher derivative contributions to the 11D M theory supergravity effective actions and reduced this on the Calabi-Yau fourfold and subsequently uplifted to F theory to get alpha prime corrections to the Kähler coordinates and the Kähler potential. And these look like this long expression. And the key objects here are these Z and T, which are essentially integral. Z is essentially a topological quantity which just arises from the third Chern class of the Calabi-Yau fourfold. And T alpha can be written as some Debiser integrals, which also include, in particular, the curvature of the B3. So these give corrections to the Kähler coordinates and the Kähler potential that are what we want to investigate now. So let's look, for instance, at the Kähler coordinates, the volumes of the base devices. Here I marked the terms which are potentially offensive in red. And so if we recall the limits, we need to ensure perturbative control by, in particular, looking at these red things, at red terms. The other ones I can ensure you that are no problems if these reds are under control. So we need perturbative control, in particular requires that these ratios here are smaller than 1. And if you now look at just plug in the classical limit, you will indeed find that the condition is violated for the coefficients of Z0 and T0, which grow which grow in this limit and thus are not under perturbative control. So perturbative control is lost if Z0 and T0 or not T0 are not equal to 0. So what happens in the two cases that we have? First, the rational vibration. So in generic models, we have actually for rational vibration that Z0 is not 0, but the precise value is model dependent. The second thing is the T0, which actually derives from k bar C0 equal 2 and is always non-zero independently of the chosen model. So we see that the classical limit leads out of the perturbative F-theory regime for rational vibrations. The story is slightly different for elliptic vibrations, where in generic models we have Z0 equal to 0 independent of the chosen model, and also T0 is independently of the chosen model. So that actually all alpha prime squared corrections that we're looking at here vanish, or that are offensive in these limits vanish, and so that the classical limit stays in the perturbative F-theory regime. So what are the consequences?
Max,
so we see
there are 5 more minutes.
Okay, thanks. So we see that there's a significant difference between the T2 vibration and the P1 vibration. So as I said before, in the case of a T2 vibration, we get a fundamental type TB string. And this is actually not a surprise that here the emergent string limit is protected from quantum corrections, because we have an enhanced n equal 2,2 worldsheet symmetry, supersymmetry, such that all order alpha prime squared corrections are expected to be absent. And also we have that the string excitations are not charged on any gauge symmetry, so that we don't have to worry, so that they don't play any role for the weak gravity conjecture. On the D3 brane, on the P1 fiber of a rational vibration, we get a heterotic fundamental string. And we saw that the classical emergent string limit is obstructed. So, and in particular, the quantum corrections affect the gauge coupling for any gauge theory along any divisor S, because we see that we actually leave the non-perturbative limit, since the perturbative corrections are way bigger than the classical value, and thus enter a non-perturbative phase also for the gauge theory that is realized in this model. So we also have no weak coupling limit anymore, as opposed to what we expected classically, to have a tensionless string and a weak coupling limit in these cases. Following this trajectory in this non-perturbative phase, we can also not ensure that the heterotic string itself, that we assume to be the fundamental object in this emergent string limit, is stable. So, but to get a weakly, or to keep a weakly coupled tensionless heterotic string limit where we don't have to worry about these things, we can slightly rescale our limit. And in particular, there's one choice for an overall rescaling mu that gives us m hat over mkk order 1, which is marginally allowed by the quantum correction. So we only have numerical suppression, but no parametrically suppression in lambda of these of the alpha prime corrections in these limits. Also in these limits, there are no further obstructions due to non-perturbative superpotentials. So we can just trust our weakly coupled tensionless vanilla heterotic limit. And one can now wonder, since the alpha prime correction are only numerically suppressed, is the weak gravity conjecture relation affected by the quantum corrections? And therefore we should look at the geometric part of the weak gravity conjecture, which is essentially the heterotic VC0, which is the heterotic string scale, times Vs, which is is 1 over the G-Young-Mills coupling squared, and VV3, which gives the Planck mass. And we should look at this classical relation, which is true classically, and look at the alpha prime corrections to these quantities here. So here I summarized the corrections to these 3 quantities that are important for the weak gravity conjecture, and everything works out fine, such that the leading order weak gravity conjecture is still fulfilled, except for these two terms, delta 1 and delta 2, whose precise form we don't need here. It's just important that they're here and correcting VC0 and Vs. The problem is, while delta 2 is suppressed in the lambda going to infinity limit, which just to leading order doesn't spoil the weak gravity conjecture, delta 1 is suppressed. So how can we say something about delta 1? The solution is, since we know that we can trust F-theory heterotic duality in this limit, because there are no major corrections to this limit, we know also that the classical relation that is written up there is equivalent to an expression for the heterotic gauge kinetic function at tree level, which just says that the heterotic gauge kinetic function at tree level is given by the heterotic 4D dilaton. Then we also know that the latter relation only receives corrections at one loop. And if one now investigates this delta 1 term closely, which the details will be in the paper, one sees that this cannot be understood as a one loop correction. So heterotic F-theory duality actually tells us that this delta 1 should be 0. And is this now possible? Because after all these alpha prime corrections come from higher derivative contributions from M theory and Calabi-Yau fourfolds, where in the M theory regime, we have delta 1 is not equal to 0. This is just a result of Grimm, Weissenbacher, Meyer, and Weissenbacher. But as it turns out, this term delta 1 can be seen as a one loop correction when compactifying the 4D F theory effective action on an additional S1, and is actually not, while it is fixed in the 3D M theory picture, not fixed in 4D F theory. So we see that heterotic F theory duality gives us the constraint delta 1 equal to 0, which on the one hand ensures that the weak gravity conjecture is fulfilled to leading order in lambda. But on the other hand, it also gives us a non-trivial constraint on the uplift from M theory to F theory at one loop. One might then worry about higher order corrections that might still give corrections to weak gravity conjecture, but then one should also probably take into account the mass corrections to the mass of the string excitations themselves. So let me summarize again with my 3 points that I wanted to raise. First, that in equidimensional infinite distance limits in the Kähler modular space of F theory and Calabi-Yau fourfold, there is always a unique emergent string. Then F theory alpha prime corrections ensure that we don't have any weird limit in our modular space where the KK scale is bigger than the 4D string scale. This actually means that finite volume limits for rationally fibered B3s are out of perturbative control, but allowed for elliptically fibered B3. And finally, we showed that the gravity conjecture relation still holds in the presence of alpha prime correction, and derived these constraints in the form of the alpha prime corrections. And I think with this, I will stop. Thank you.
Thank you very much, Max, for your nice talk. Questions, please, from the audience.
I have a question. Yeah, I just missed one thing. When you say, I think I missed what you mean when saying that the weak gravity conjecture is modified by quantum corrections. Do you mean that the extremality bound of the black holes is modified, or you mean that the charge to mass ratio of the states is modified, but the bound remains the same, or both are modified, or what's going on? What are you expecting?
So what we're taking is whether the charge to mass ratio of classically fulfill the weak gravity conjecture is corrected simply by if this relation between the three geometric quantities is changed. So the question here is, do we still have this this classical relation, essentially that the charge squared over mass squared is equal to m Planck, or 1 over m Planck? And this is what we checked here, because if the other question is, if we would find corrections to this relation, then this should also correspond to some change of the black hole solution, like the ones you have for heterotic black holes at order alpha prime heterotic. But what we looked at here is the change of the charge to mass ratio of the super external states.
Okay. Okay, thanks.
Further questions, comments, please. More comments?
And I have a naive question. Although I'm not a string theorist, is it possible to expect some emergent type 1 string theory, for example, if you consider a different setup?
So the question is if I can expect an emergent type 1 string.
Yeah.
yes, you can think of this, at least we have this in NREQ 2, we observed this, that if you have, for instance, type 1 string theory on K3 times T2, then you can take some limit of the T2, and there you would actually get an emergent type 1 string, which is, but in that case, just a heterotic string again in disguise. So there's not much, so it's very similar in essence to the cases that I looked here, because the type 1 string is just dual to the heterotic string, if we consider K3 times T2.
Okay, thank you.
Any further comments or questions? I don't see any at this stage, so let's take the opportunity. Yes? Hello? No. Okay. So let's take the opportunity to thank Max again for his nice talk. And we move on to the third speaker and final speaker of this morning session, Mohsin Karkaran. Hello, good morning.
Good morning.
Or
So
good afternoon, good evening in your case.
So can you see my?
Very good. Okay. Yes, perfect. So again, welcome to Mohsin Karkaran from IBS now, previously Virginia Tech. And he will tell us about heterotic complex structure moduli stabilization via spectral data. Please, Mohsin.
Okay. Thank you for giving me the opportunity to give a talk here. This talk is not directly related to the Swampland, but it's kind of more related to a string phenomenology. And this is based on a paper that we are going to publish with. Excuse me.
Mohsin, sorry, now your screen is black. Is that intended?
Oh. Is it? Can you see now?
I can't. I'm seeing the your browser. But not now. Perfect. Yes. Very good.
Okay.
Sorry.
Okay. So this is not directly related to the heterotic Swampland, but it's mainly related to a string phenomenology. And it's based on a paper that I'm going to publish with Wei Chui, a former student at Virginia Tech. So in general, you all know that in a string compactification, when you compactify the theory in a effective theory, you get a lot of moduli basically, which corresponds to the fluctuations of the fields and geometry of the compactification. And the number of them can easily goes up to several thousands. And so people, in order to get rid of them, usually try to find some mechanisms to generate some potential for them to make them massive, basically. So in the case of the complex structure moduli, basically the fluctuations in the shape of the color VO in the heterotic string. In this paper, Anderson, Gray, Lucas, Avruth showed that they can use the holomorphicity of the gauge fields that live over the color VO to basically stabilize at least partially the complex structure moduli. And basically the math that they use is Atiyah class computation. But the models that they construct are very limited. And also they don't show exactly, in case of, there is, for example, if F theory dual, how exactly this stabilization can be mapped to the similar scenarios in, for example, F theory. So our goal is to just find some more general examples and in principle see how it can be connected to the F theory. If I have time, I will explain more. So the general idea everyone knows, I mean, we have a heterotic theory in 10 dimensions. We want to compactify that to get a n equal 1 supersymmetric for the effective theory. We want n equal 1 for the basically to have a chiral theory. And if I assume in particular that in the edge flux is 0 over the colobio and the dilaton is constant, then it means that the internal manifold that we compactified the space on that should be a colobio. And in addition to that one, we also have some background gauge fields living over the colobio. And again, in qual one supersymmetry in the effective theory, put some constraints over the basically gauge fields. So basically, the first two means that the corresponding vector bundle with this connection, with this curvature, should be holomorphic, and the other one means that the vector bundle should be stable. So how we can construct such kind of things? So basically, we want a colobio, and we want a vector bundle living over that. And that vector bundle should be holomorphic, stable, and if we want E8 vector bundles, it should be also degree 0. So how we construct such kind of vector bundle? If I assume further that the colobio is Weierstrass elliptic fibration, basically there is a projection, there is a surjection from X, the colobio, to the surface, such that the fibers are elliptic curves and we have a section. Then in this case, we can use Fourier-Mukai to construct a vector bundle. Basically, Fourier-Mukai is basically some fancy Fourier transform, and it's just some automorphism between the Dirac category of the X to itself. And in case that vector bundle is basically degree 0, and at least its restriction to the fiber is stable, then the image, the Fourier transform of the vector bundle will be a torsion sheaf. Basically, it will be a line bundle that is restricted over a surface, basically. So if in this painting that we have, if this is the total space of the elliptic fibration, then the fibers are basically elliptic curves, and then we can embed a cover of the base inside this elliptic fibration, which we call it a spectral cover, and the degree of that cover corresponds to the rank of the vector bundle. And we have a line bundle over this. Now, and also we can use the inverse transformation to construct a vector bundle. So there is a one-to-one correspondence between the vector bundle and this spectral data. And we can translate the stability and holomorphicity of the vector bundle in terms of this spectral data. For example, if the spectral cover is smooth or at least a reduced surface, we can show that the corresponding vector bundle is stable. And this is what we assume from now on. So basically, the vector bundle is always stable in the future. And also the holomorphicity of the spectral cover and the line bundle over that can correspond to the holomorphicity of the vector bundle. Now, basically, we have three kinds of moduli in the heterotic model, right? We have a complex structure moduli, we have the fluctuations in the gauge field, and we have fluctuations in the Kähler moduli. And for the Kähler moduli, we don't care because we assume that the vector bundle is actually stable. So it doesn't have any correlation with the Kähler structure stabilization at this point. So the main point in the paper in 2010, I mean, Anderson, Gray, Andre Lucas, and Alwood was basically if I consider the simultaneous fluctuation of the complex structure and the gauge field, then if I want to keep the holomorphicity condition, then the fluctuations should satisfy this equation. So basically for a given fluctuation in the gauge field, not all of the complex structure fluctuations can satisfy supersymmetry constraints. And they show that using this Kukov-Wafel-Witten type of superpotential, where omega is a top 3 form, and omega 3 is just a Chern-Simons term related to the connection. Then if I just consider the simultaneous deformation of the complex structure and the gauge field, then for those complex structure deformations that doesn't satisfy this condition, we have a corresponding F term in the F term potential in the effective theory. And mathematically, they show that basically these simultaneous fluctuations are elements of a homology of H1 of X and Q, where Q is just the ATS sequence. So to make a model that actually we can see the stabilization, they construct a SU2 vector bundle, and which is a extension of two line bundles, basically. And basically, to make sure that this vector bundle actually is really a SU2 vector bundle, we should look at the extension class of this one. Each element of this extension class corresponds to a particular SU2 vector bundle here. And they show that there are some subloci in the complex structure moduli space that you get some new elements inside this extension group. So basically, if I choose those new elements, then it means that I have some particular vector bundle that is defined only on the sublocus in the complex structure moduli space. And then they show that if I move away from that one, because they also fix the Kähler structure such that the vector bundle cannot become a split, then if I move away from that locus in the complex structure moduli, the vector bundle must become non-holomorphic. So basically, the directions normal to that locus in the complex structure moduli is now stabilized. And then they show that due to this Bukov-Witten superpotential, in principle, you may get some, you can see how the corresponding F term should show up, which I'm not going to the details, but you can see the details in this 2011 paper. But as you see, this example is very limited, and it's just a SU2 vector bundle. So basically, they are stabilizing partially the complex structure moduli in a E7 effective theory in 4D. So, but the general message is that we can find some sublocus that it is possible to define some particular vector bundles over there, such that if you move away from that locus, the vector bundle becomes non-holomorphic. Therefore, that basically a normal direction in the moduli space is a stabilized by supersymmetry. So, in order to understand this a little further, we can consider in a case that the colobia is actually elliptically fired. In that case, if the vector bundle is given by this extension here, the sigma is the section, and dB is the base divisor in the base, then again we should look at the extension group to see whether this vector bundle is actually SU2 bundle. And then we can use some Lie spectral sequence calculation to show that actually it decomposes into two subspaces given by these cohomologies in the base. And then after some Fourier-Mukai, by acting the Fourier-Mukai over this sequence, we can actually show that that the coefficients of the spectral cover actually are in one-to-one correspondence with the elements of this extension group. Here, X is the coordinate X and capital Z are coordinates of this Weierstrass elliptic vibration. So these coefficients corresponds to the extension groups actually. And then it means that when we are on a subloci that the extension jumps, it means that we have we can define some new spectral covers. And when we move away from that locus in the complex structure moduli, the spectral cover is not an algebraic surface anymore. So basically, it's not a holomorphic cycle anymore. So the corresponding vector bundle becomes non-holomorphic, and therefore it is unstable. Therefore, it is stabilized. So basically, now because it is given by the spectral data, we can map this one in principle to the F theory. In the F theory dual, we have some Higgs bundle. Inside that Higgs bundle, we have some spectral data, and they showed that the coefficient of the spectral cover, both on heterotic and also on the 7-brane data, actually map to the Casimirs of the Higgs field inside the 7-brane gauge theory. So basically, and also they show that there is a superpotential like this one, similar to the Bukov-Wafel region. So it means that on that loci that we have new elements inside the extension group. On the F-theory dual, we have new elements inside the Casimirs of the. We can have new terms in the Casimirs of the Higgs field that can, if we move away from that loci, it makes the corresponding flux non-holomorphic. So to give an example, consider a surface like this one, where it is a hypersurface inside a P1, P2 space. And the generic defining equation of that one is given by this. So now suppose dB is just a base divisor here, is given by this divisor. For generic P, we can show that the only possible spectral cover is the first one. I mean, it's just this step. But if we now restrict the defining equation to this form, such that this P3 term is 0 now we have an extra term in the spectral cover. So if I choose this spectral cover on this special locus of complex structure moduli, I cannot move away from this locus, because then it makes this surface non-algebraic. And then it is not, the corresponding vector bundle is not holomorphic anymore. So it means that the directions corresponding to these P3 terms is stabilized in the complex structure moduli. So now we have a way to generalize this. Basically, we can consider a spectral cover, which is degree n, corresponding to the SUN vector bundle. And then we should look for the points in the complex structure moduli where we have new terms in these coefficients of the spectral cover. But then the question is that how we are supposed to find such a locus. So one way is to look for the Noether-Lefschetz locus inside the moduli space. Basically, Noether-Lefschetz locus are the points in the moduli space such that the Picard group actually jumps. So Noether-Lefschetz are the loci that the Picard group actually jumps. So we have actually new divisors inside the space. Basically, we have divisors that are not induced from the ambient space. So, for example, consider this space, which is defined as a hypersurface in this toric variety. And generically, the equation is given by this. So we can, the H11 of this one is 8, but the Picard number of this one is 3. We have 3 independent divisors. And we can view this actually as below up of the first Hertzsprung surface, F1, on 6 points. But because we are blowing up all of these 6 points together, it means that they are not independent -1 curves. We can blow them down and blow them up together, up at the same time, all of them. So now consider this reduced form of the defining equation, where the second term corresponding coefficient of x2 is now reducible. Then, after doing some conifold transitions, we can show explicitly that the Picard number here is actually 4. It is increased by 1. And the initial exceptional divisor, which was union of 6 - 1 curves, now gets separated into 2 sets of 3 - 1 curves. Basically, it becomes the sum E1 plus E2, where each one of them is 3 - 1 curve. Now we can consider a spectral cover that depends explicitly on only one of them. Then this spectral cover is now only defined over only with this defining equation. So again, moving away from this locus is makes the vector bundle non-holomorphic, so it is stabilized. So we are forced to consider this reduced form of the defining equation, and so some complex structure moduli corresponding to that is actually stabilized. So another thing that we can do is that basically we can consider some locus that the Picard group of the Picard group of the spectral cover itself jumps. or basically we are looking for Noether-Lefschetz loci on the on the spectral cover modulated space. So to do that, consider a generic elliptic vibration like this one, which is given by Weierstrass, and then we are assuming that now this G, the coefficient G, is now gets reducible like this. So therefore, we have a curve C inside this space, which is not complete intersection anymore. It's just a curve in the ambient space that, because of this special complex structure, lies inside the colloquium. So this curve generically only intersects a spectral cover at finite number of points. But if I assume that the coefficient A0 of the spectral cover actually gets reducible like this, then this curve C lies inside the spectral cover too. So we have new divisors inside the spectral cover. So in principle, now we can assume that the line bundle over the spectral cover can depend on this divisor. So if I assume that the topology of the vector bundle is given by this equation, then it means that basically after doing some Fourier-Mukai and computing the topology, the first Chern class of the line bundle will depend on this divisor explicitly. So basically, now we cannot move the G to a generic form anymore. Because if I do that, the divisor here will disappear. And then the corresponding divisor actually disappear. And then this line bundle over the spectral cover becomes non-holomorphic. So this time is the line bundle that becomes non-holomorphic and the vector bundle becomes non-holomorphic. Also, at the same time, if I just keep the G reducible like this form, but now I deform the spectral cover back to a generic form, then it means that, again, the line bundle is becomes non-holomorphic, but this time the vector bundle modulated space is stabilized. So this example can stabilize both vector bundle and complex structure. So if I just map this one in the F theory, both of these cases are not new actually. If I look at this Brown-Colinucci Wallenberg paper, the corresponding situation looks like the algebraic four fluxes that we can get from the F theory dual geometry. Also, in a paper by Donaghy Weinhold, they used this one to stabilize the spectral cover, the spectral data of the Higgs, the Higgs bundle data. Actually, I mean, they wanted to make the flux inside the 7-brane non-holomorphic, and also they used similar ideas there. So now the only thing is that the future directions. So far, we only assume that the spectral cover is given by a non-reduced. I mean, it is either a smooth or at least a reduced surface. Reduced means that basically non-reduced surface is like a stack of branes on top of each other. That kind of surface is a non-reduced surface. But when it is only one, it has only one multiplicity, it is a reduced surface. And when the spectral cover is reduced, the corresponding vector bundle is stable. But if we assume that the spectral cover can have non-reduced components, then we have the question of the stability too. And then we can use that one probably to basically stabilize, or at least partially, the Kähler structure. So it is possible to, probably it is possible, we haven't found it yet, that if we consider a general spectral data, we may be able to stabilize all of the theory modulated spaces in the heterotic, at least partially. And the other thing is that since we can map this one to the F theory goal, it is possible to, if there is a same limit, maybe it is possible to study the correspondence of this kind of modular stabilization with the type 2 or intersecting brane setups in the weak coupling limit of the FT2. But I'm not sure whether there are something new in this, but at least we can find a clear correspondence between, clear relation between these two types of stabilization, between heterotic and non-heterotic. So that's it. If you have any question. Anyway.
Yeah, but before, let's thank Moshe for his very nice talk. Yes, please, questions. Questions from the audience. Maybe I can start. So you said at the end that you expect that it might be possible to stabilize all the moduli. So even if we stay on the side of the complex structure moduli, can you estimate how expensive this procedure is? Because you need to, you have certain constraints, right? Tadpole or Bianchi identity constraints for the construction of the bundles. So you would probably need many bundles. And do you think it is possible to do that without overshooting in order to get constraints on all complex moduli?
Yeah, probably. We can construct only one of the vector bundles, and we must construct another vector bundle to compensate for the tadpole and anomaly cancellations, for example. But I think even only one of these vector bundles, if the spectral cover is generic enough, can put a lot of constraints. I'm not saying it totally stabilize everything, but at least can partially stabilize Kähler structures.
Mm-hmm.
I mean, if the spectral cover has some non-reduced components, actually.
Mm-hmm. Mm-hmm. That's interesting. And does anything change if you look at bundles with non-vanishing first Chern class? So then you also get the integrated D term or the trace over the D term. It's not only your stability condition. Does this add anything interesting, or is this just another?
Well, if I want to construct it in terms of the Fourier Mukai, at least it should be relatively degree zero. I mean, its restriction to the fiber should be flat. And so the Chern class cannot be zero, have to be zero over the fiber. So as long as that is satisfied, I think same conditions, same story can apply there.
Okay, thank you. Are there any other comments or questions from the audience? I don't see any right now. So if there are no urgent questions, then I think we can go into the break, which will be a break of 10 minutes, if I understand correctly. And of course, we can continue discussion over the break, I suppose, via the chat. And before, let's thank Moshe again for his very nice talk and all the speakers of the first morning session.
Okay, so we have Joe Conlon here, who's going to talk about modular stabilization and the holographic Swampland. Yeah, go ahead.
So, thanks. So sorry about this thing with the screen. So just to confirm, is the screen? Do I ask for the pages to be shifted, or can I?
No, unfortunately, I have to shift the pages for you.
Yeah. Okay. Good. Yeah. So thanks very much for the invitation. Sorry about this trouble. Slight trouble. So what I want to talk about is the Swampland in the context of holography, in particular, kind of see if it's possible to apply various ideas of the Swampland to the ADS Lagrangians that one gets in moduli stabilization, and saying, can one probe, whether or not certain modifications are in the Swampland. Okay, so if we go to the next slide. Okay, thanks. So the ordinary way most moduli stabilization kind of works is there's this logic where one starts with the string theory, then one turns this to a 10-dimensional supergravity, then one turns to a 4-dimensional supergravity, and you progressively use the arguments and logic of effective field theory to integrate out modes, reduce things to various effective potentials, and at the end, one ends up with, one has a four-dimensional effective field theory where you've got a potential as a function of moduli with a small number of fields left over compared to the field, everything one originally started with. And then claims about, de Sitter vacua, connections to cosmology, or whatever, they all ultimately often tend to rest on these four-dimensional Lagrangians. And so part of the Swampland program is the challenge to, this methodology of effective field theory, and to say, well, and so the kind of motivation for this work is to then say, well, are there things, can one look at these four-dimensional Lagrangians? They're often in ADS space because most de Sitter constructions start with an ADS construction. That's true in KKL2T, it's true in LBS, it's true in lots of cases. And say, if it's an ADS Lagrangian, then one should be able to connect to a CFT, and can one probe whether or not this thing makes sense or not? Or whether or not things which would obviously be wrong, is there any sign that they're obviously wrong? Okay, so sorry, next slide. Thanks. Okay, so just a very brief review of moduli stabilization, and because one thing I'll be using is the large volume scenario. One reason for using this is because it tends to stabilize at a very large value of the volume. Then in some things, advantages and difficulties can be clearer in this limit. Because if the volume is asymptotically large, if the volume is like 10 to the 10 or 10 to the 15 or something, then it sharpens various questions because you've got genuine scale separation between the KK modes, the string modes, and the moduli, etc. So other than just recalling this and saying that you've got a potential that leads to very large volumes, I don't really want to discuss the details of how the stabilization goes. So next slide, please.
Sorry.
Sorry. Okay, so yes, so the point of using the LDS is that because the volume gets to be extremely large, you've got a excellent parametric decoupling, so you've got a clear separation between the various modes in the problem, and there's a clear geometric origin to this, so we can use our geometric intuition to say that you've got a very large compact space and that you've got a very good separation of the various different scales in the problem. Okay, next slide, please. Right, okay, so in terms of holography, so what we want to have is we want to have an ADS minimum. So you've got an ADS Lagrangian and you've got fields in ADS, and then then these fields have interactions, and then in principle, this then gives you, using the ADS-CFT language, a map onto various properties in a putative dual CFT. So we're not going to obviously aim to be construct the CFT and say what is the microscopic CFT. We're saying, assuming that you have an ADS Lagrangian, assuming this really exists as a string vacua, then if you try and reformulate this in the language of CFT, what do you get and what can you say? So what I've done here is I've I'm just asking you to basically accept here what's the effective theory in LBS for the two lightest fields that are left over. You've got the volume modulus and the axion, and these fields are, well, there's a graviton as well, but of the moduli, these are parametrically the lightest fields. So you've got a potential for the volume modulus, you've got kinetic terms for both, and you've got a coupling of the volume modulus to the axion via the kinetic term. Okay, next slide, please. So what one does is one just has to, we want to solve for the minimum of the potential, and then expanding about the minimum, you get the masses of the fields and their couplings. So this is what we normally do in moduli stabilization, but because it's an ADS Lagrangian, we can also think about saying, right, so what would this correspond to from a CFT perspective? Okay, so one thing I also want to just highlight here is just looking at the kinetic term and the exponential with the modulus. That it goes as the minus e to the minus phi. Of course, we think this is obvious, but because it means that the equivalent to the axion decay constant going to 0 as you head towards a large volume limit. But I just want to note that at this point because I will return to it later. Okay, next slide, please. Okay, so in CFT, if you've got the CFT, the scalar field on ADS, the scalar field has a certain mass, and then in the dual CFT, this corresponds to two operators with a conformal dimension that for compactifications to ADS4 is related through this equation. Delta on delta minus 3 is basically the mass squared times the ADS radius squared. And so for this case where you've got ADS4, which would correspond to CFT3, we can put modes into kind of three basically different categories. We can say they're basically what I've called heavy, light, and interesting. So heavy modes are modes which are basically parametrically heavy compared to the ADS scale. And in the LVS context where we can basically imagine the volume getting really, really large. So such modes, their conformal dimensions is basically parametrically decoupling. So if the volume is these have conformal dimensions which are basically parametrically larger than unity. So examples of those are obviously things like the KK modes and the string modes, but in LVS there's also things like the complex structure moduli, the gravitino, and the small Kähler moduli. So quite a lot of the modes fall into this category. The other thing in modes which are light, so these are modes which are parametrically lighter than the ADS scale, and for these their conformal dimension basically goes to 3 because the mass squared goes to 0. And so the conformal dimension goes to 3. And the other thing is the kind of ones which I call interesting, which are modes which basically remain, so their mass is basically parametrically similar to the ADS scale. And these are conformal dimensions that are going to be order unity. Okay, so next slide, please. Okay, so in LVS, what happens if you look around the minimum is that the heavy modes are the KK modes, the complex structure moduli, and all the Kähler moduli except the overall volume. So the fact that the complex structure moduli and almost all the Kähler moduli are ending up being classified as heavy is a legacy of the kind of the no scale structure that's there that makes certain modes and the scale of the potential lighter than it would otherwise be. The modes that are light are the graviton and then the overall volume axion. And the overall volume modulus one is kind of interesting in that it's basically parametrically similar to the ADS mass. Okay, next slide, please. Okay, so if you look at LVS in a limit where the volume gets to be extremely large, so you imagine that you've stabilized the volume such that the volume is 10 to the 15, 10 to the 20, 10 to the 25, or something of that similar. These may not be phenomenologically realistic, but it's interesting in terms of thinking about these matters. So then you find something quite nice, which is that the conformal dimension of what would be dual to the volume modulus, it basically goes to essentially a unique value, which is basically 3/2 on 1 plus square root of 19. And so you've got a rather kind of fixed prediction. Well, not prediction isn't really the right word, but you've got rather a fixed values for what the conformal dimensions would be in the kind of corresponding 3D dual CFT. So I repeat, we don't have a construction or a microscopic construction of the CFT, but if it does exist, this is what the light or the low dimension operators would be, and what their kind of parities and their conformal dimensions would be. And this is kind of a feature of LVS that isn't true, for example, for KKRT, which doesn't have fixed conformal dimensions. Okay, and next slide, please. Right, so one thing I think is then interesting and is attractive reason to study, kind of think about LVS from a holographic point of view, is that because it offers kind of these fixed dimensions, and it's kind of reasonably well motivated. So it gives you something which from a CFT perspective would be rather fixed, and it's got a small number of low dimension fields. And also as the ADS Lagrangian is fixed, then this means that things like the CFT 3-point functions, the CFT correlators, are in principle also fixed. That doesn't mean that they're kind of easy to work out what they are. Next slide, please. Okay, so now I want to come back to the kind of this topic of this workshop, the Swampland. So I want to kind of highlight, I'm going to focus particularly on one, there's one particular issue I'd like to highlight here, which is it's the sign of the kinetic term for the axions. Now, in terms of the stabilization, the volume axion doesn't really play any role. It has no potential. It remains massless. Yeah, it doesn't really play any role in what's going on with the stabilization. One thing that you have is you have the kinetic term. The kinetic term goes to 0 as the volume goes to infinity. This is completely as you would expect. And this is equivalent to having this minus sign in the exponential. So this e to the minus square root 8/3 phi over m Planck. It's telling you that as phi, which is the log of the volume, gets big, then the kinetic term for the axion gets small, and that's exactly as you would expect things to behave. Okay, so this is now whether LVS, you can have deep questions about whether or not things like LVS, whether there's any subtle problems with them. But one thing where I think, from all we know about string compactifications, there's a very clear problem would be is if I take that minus sign in the exponential and then swap it to a plus sign. So next slide, please. Okay, so this is just sort of point of view the ADS theory. This is a small modification. I've changed the minus sign to a plus sign, but we kind of know this is in the swampland. This is equivalent to an axion decay constant that would diverge in the decompactification limit. Would go to be parametrically transplanckian. So clearly this is wrong, and clearly this is in the swampland. Yeah. Now, note that this doesn't lead to like a runaway potential for the modular, or it doesn't lead to anything obviously going wrong with the potential. You still have a potential, there's no potential for the axions, but clearly this kinetic term is behaving the wrong way. And so clearly this is in the swampland. And then, so the thing that kind of motivates this is then the question of, is there something we can kind of pick up on if we translate this ADS theory to a CFT language? So does this kind of making this thing go wrong, does it correspond to anything in the CFT? Yeah, and then the longer term goal, or the longer term dream would be that, could one, from a CFT perspective, identify stuff that kind of marks these theories out as in or not in the swampland. Okay, next slide, please. Okay, so more generally, so just expanding out, so saying that from a perspective, something to translate things to a CFT. So you've got an ADS theory where you've got masses and then you've got interactions. And so the interactions come in two forms. They come in the self-interactions of the volume modulus. So this is just expanding about the potential and working out the 3-point function, the 4-point function, the 5-point function, and so on. And then you've also got in the kinetic terms, where you've got couplings between the volume modulus and the axion. So on this slide, so the first line is then expanding out the endpoint functions or interactions of the volume modulus. And the second line is then expanding about the kind of the higher point interactions in the kinetic term for the axions. And this is in the kind of basic LVS. If you had the sort of swampland version, you would change that minus √8/3 to a plus √8/3. And so from a CFT perspective, this is like a generalized three theory. And then the interactions would, these interactions would correspond to giving rise to structure constants in the CFT, which then would affect the CFT correlators. Okay, so next slide, please. Okay, so what we're doing is then the question we want to ask is if we modify the interactions of the volume modulus and the axion, so particularly in the kinetic terms, then we feel pretty confident this is in the swampland. That this is going to be in the swampland because it leads to an axion decay constant that diverges in a decompactification limit, and we know this is we know this doesn't work. This is not how string theory behaves. But then can we say what is actually wrong with this, or can we identify something that would actually be wrong with this? Okay, so next slide, please. Okay, so let's just sort of frame what the problem we've got is. That we've got a generalized three theory with some corrections. So this is the CFT. One which we think would be a consistent theory, but then if we change the sign, then we would have something which is in the swampland. And so the question we want to say is then, can one correlate properties of the CFT with this change from the consistent theory to the swampland theory? Okay, so next slide, please. So where can this come from? So I mean, what in the CFT could we pick up on that might be sensitive to this? So okay, so the first thing is this, so we're going to focus mostly on 3-point interactions in the end. So this is like taking the leading sign, the first sign, rather than, even though in principle we had like expansion, 3-point functions, 4-point functions, 5-point functions, etc. It's simpler just if we focus on the question of the 3-point functions. So the 3-point functions in the ADS theory on the holographic dictionary are kind of relating to 3-point structure functions in the CFT. Now, clearly the signs of the 3-point functions by themselves are not determinate, because if you do a change in a field redefinition, if you about the minimum, you expand about a minimum and you exchange phi to minus phi, then that will flip the sign of a 3-point function, but it's clearly not a kind of particularly physical change because it's just a field redefinition. So the 3-point functions by themselves are not quantities that we think might be interesting. So, but something that kind of is more kind of physically invariant are anomalous dimensions of operators in the CFT. And so this is what we will focus on. Okay, so next slide, please. Okay, so the CFT, so we've expanded about the ADS minimum. You've got and just take the 3-point function. So we've got the cubic term for the volume modulus, and then we've also got the leading kinetic term for the coupling of the volume modulus to the axion. So just to note that what the sign of these are telling us is that the sign of the kinetic term, this is basically the physics this is picking up on, is that the kinetic term decreases as you move to, sorry, the decay constant decreases as you go to large volume. The sign of the cubic term is telling you that the mass of the volume modulus decreases as you go to large volumes, or the curvature in the potential decreases. So both of these, there's good reasons for the signs they do. And then translating these to CFT, then you would have these structure constants. So this is using, I'm not going to discuss in detail where the expressions come from, but they're pretty standard from a CFT perspective. But then, as I said, that these, you can all clearly flip the sign of these. A redefinition, if you're expanding about the minimum phi to minus phi, obviously doesn't change anything physical. Okay, so next slide, please. Okay, so the one thing that are well defined are in the CFT are anomalous dimensions. And so these are the anomalous dimensions of what are called like the double trace operators. So we're putting together if we put together, say, the two volume moduli, or a volume modulus and axion, or the two axions, this gives us a double trace operator. Physically, these are kind of related to, correspond to kind of like binding energies of the two particle states in ADS space. And the anomalous dimensions can be computed, or they can be related to by using what's called the Mellon amplitude in CFT. So the Mellon amplitude is the kind of the analog for the analog in ADS space of the kind of the Feynman amplitudes in regular Minkowski space. And and it can be computed using there's a similar set of rules in the way that you have the Feynman rules. There's a similar set of rules for how you compute the Mellon amplitude for a CFT. And given the Mellon amplitude, you can then use that to extract the anomalous dimension of the double trace operator. Okay, next slide, please. Okay, so for a 2-to-2 process, so the diagrams that can compute, the diagrams that can contribute to the evaluation of the Mellon amplitude are just like with the Feynman diagrams. There's this kind of the S, T, and U diagram, and then there's also a quartic term. In the kind of the quartic term, the direct quartic interaction only contributes for low values of L. So the double trace operators are indexed by kind of quantum numbers N and L, where L is kind of an angular momentum one, and the quartic one only contributes at small L. For the other ones, it turns out that the kind of the diagram that really matters for the contribution of the Mellon amplitude to the anomalous dimensions is the exchange diagram. Kind of an intuition you can have for this is that because the anomalous dimension kind of physically corresponds to like a binding energy in ADS, and if things are kind of well separated, if you've got a two particle state and the particles are well separated, then exchange is what gives you the binding energy of that state, rather than things like S-channel diagrams, which are corresponding to things like annihilation. Okay, next slide, please.
You have 5 minutes.
5 minutes, great, thanks. Okay, so skipping to where the kind of the results for the anomalous dimensions. So I said originally there are two light scalar fields. There's the volume modulus and the axion. So the volume modulus with itself and the axion with itself is not so interesting. Essentially, this is because the sign of these is always fixed because they involve the square of a 3-point coupling. So that basically ends up with a fixed sign. The more interesting one is the mixed double trace anomalous dimension, which corresponds to the volume modulus and the axion. And Okay, I've given you the expression for what this looks like here, and this is interesting because it's sensitive basically to the product of the volume coupling with itself and the volume coupling to the axions. So this is then, the sign of this is then sensitive to the signs of these couplings in the ADS Lagrangian. Okay, and so next slide, please. Okay, so the equation on the top left here. So what things then reduce to is that the sign, large L sign of the mixed double trace anomalous dimension basically depends on these couplings in the Lagrangian. So for the kind of standard couplings, you've got a negative anomalous dimension. But if you flip either of these three-point interactions to ones that would correspond to a Swampland theory, then the anomalous dimension switches sign to a positive anomalous dimension. And this is interesting because, in certain cases, so not for mixed operators, but for certain double trace operators, it is known that you have to have negative anomalous dimensions within the CFT. But I stress it doesn't apply as a theorem for the mixed ones. So a slightly interesting thing as well is that with LVS in the large volume limit, and I don't know whether this means anything or not, but it's certainly interesting. The anomalous dimension for the dimension for the volume modulus is kind of about 8.03. And this expression for the sign of the anomalous dimension basically switches sign at 8. So it corresponds to, if you just did nothing else and just changed the value of the dimension for the volume modulus, then it would be positive up until 8, and then it flips sign to being negative just immediately after you pass 8. Okay, next slide, please. Okay, so in an LVS context, what it turns out is then, so the right signs of the 3-point ADS couplings, i.e. ones that aren't sending the axion decay constant to infinity as you go to large volumes, are equivalent to having negative anomalous dimensions for the mixed double trace operator. And a similar result, in fact, holds if you look at kind of perturbative stabilization, where you've got, say, just using loop corrections, or if you're using KQRT or racetrack stabilization, you actually get the same result, that you get negative anomalous dimensions for what's the kind of the conventional thing. But then if you start taking signs in the ADS Lagrangian and fiddling them to stuff that is in the Swampland, the anomalous dimension switches to be positive. Okay, next slide, please. Okay, let me also just briefly point out there's an interesting connection to the refined distance conjecture here. So if you think about what these 3-point functions mean, the signs of 3-point functions mean. So if you consider out, say, the volume coupling to heavy fields, like their mass terms, so the sign of that coupling is basically tell you, as you go to larger volume, does the heavy field, like the KK mode, does it become lighter or does it become heavier? Because if your coupling is like phi, psi, psi, then the sign of that as phi increases is basically telling you what happens. Do the fields become light, i.e. does the Taylor states come down to become light as you move to large volume, or would the KKs become positive? So it's interesting, and there you also get the same behavior, that you get a negative anomalous dimension for the mixed operators with the right signs, the correct signs of the theory, whereas if you kind of modify with them to kind of make a Swampland modification, then the anomalous dimension is instead positive for the mixed double trace operator. Okay, so this is interesting in that there does seem to be this connection between like a Swampland modification to the ADS theory and having having positive anomalous dimensions for these mixed double trace operators involving the volume field. Okay, next slide, please. Okay, so that I think is interesting. There are many examples that then a negative anomalous dimension in the CFT for the mixed double trace operator seems to correlate to having like non-Swampland signs in the ADS Lagrangian. However, to put a note of caution on this, so when we've been looking more recently at this with for the case of fibered LVS, where we're looking at kind of correlators involving the fibered moduli, then this doesn't seem to hold. There, as axions seem to cover different signs to the fiber moduli. If you stabilize the overall volume, then you kind of have fibers, one fiber gets large, the other fiber gets smaller. And there it seems to, you can get a mixture of signs. So, okay, so I'm gonna leave open whether this is is this telling something deep? Is it just a feature of the volume modulus? Perhaps one could say, that the volume modulus is morally the extra dimensional graviton, and because gravity is always attractive, so morally, basically anything involving the volume modulus should always give you negative anomalous dimensions. That should always have the correct sign for stuff involving the volume modulus, because exchange of the volume modulus is morally like exchanging a graviton, and that should always be attractive. But there isn't something true in general. Okay, so I'm not sure what the general case. This is work in progress, but certainly in the case of the volume modulus so far, there seems to be an interesting correlation between having a negative anomalous dimension in the CFT and having kind of couplings in the ADS that aren't obviously in the Swampland. Okay, thank you.
Thank you for that very interesting talk. Okay, I'll stop the share. Are there questions? No. Okay, maybe I can ask. Can you, so by this fiber LBS, you mean some large volume manifold, but that has a vibration that can be small, or?
So with normal LVS, you have like these small fields that get basically heavy masses because they'll stabilize non-perturbatively, and then the overall volume modulus. So
like Swiss cheese, yeah.
So if instead, like the overall volume, instead of just having a single field controlling the overall volume, you have like a fiber structure. So you've got like two fields contributing to the overall volume. Then the ordinary LVS stuff basically stabilizes the combination that corresponds to the overall volume. But then a kind of a direction where fiber gets larger, like the fiber gets larger and the base gets smaller. For example, that mode is unstabilized by the kind of the ordinary LVS dynamics. So that remains as an additional light mode in the effective field theory. So then you've got an additional light field that's left over. And then that additional light field has also got a low conformal dimension viewed from a CFT perspective.
I see. Okay.
Yeah.
Any other questions?
I have a question. So thanks for a very nice talk, Joe. The LVS is a non-supersymmetric ADS vacuum. So
yes.
Does this mean that it goes against like this conjecture of Gurry-Vafra that the CFT, there should be no CFT with a stable vacuum dual, or does the reasoning depend on the stable vacuum existing in the CFT, or and can you study these things explicitly? Can one find the non-perturbative decay mode of the LVS? I don't know, all these things.
Yeah, I mean, yeah. So obviously that's kind of a very much a conjecture, and also my kind of belief on it is that if you have a vacuum which is kind of that is kind of or if the sort of the decay channels are involving kind of highly non-perturbative stuff, then or basically where the decay would take a long time, or be highly suppressed, then one ought to be able to use this at least as kind of an approximate language. I mean, because the argument that kind of if you've got a decay thing, it will decay instantly is basically one that says that stuff from the boundary of ADS can come in to the center of ADS in finite time. But this kind of relies on basically you have like totally exactly ADS. So, and on kind of physics grounds, on physics grounds, I'm kind of skeptical that these things can kind of be robust as as very strong statements. I mean, normally in physics, if you say that something is kind of enormously suppressed but non-zero, if something's enormously suppressed, you can usually use the approximation that it is enormously suppressed.
But then it cannot be a CFT dual. I mean, if it's a CFT dual, then there can be no physical scale. So that means there can be no finite time scale in the problem.
Yeah, but the problem is, so this is like, so for example, for example, QCD. I mean, regular QCD is clearly not a CFT, but CFT methods have been quite successful, for example, in working for kind of amplitudes for actual QCD. And likewise, if you take a theory that is never strictly conformal because it slows down and then it kind of walks, if you walk for 100 orders of magnitude in coupling constant, without ever actually having the beta functions being 0. I mean, strictly that is not a CFT, but you can use CFT methods to get a very good understanding of what's going on in this region where the couplings are walking for hundreds of orders of magnitude. I think that is just sort of standard physics. And so these things that say that if something is not exactly ADS or not exactly a CFT, you therefore there's no sense in which you can say it's approximately ADS or approximately a CFT. I don't really buy those arguments.
Thank you.
Any other question for Joe? No. Okay, if not, let's thank him again.
Thank you.
And our next speaker is Eduardo Gonzalo from IFT.
Hey.
Eduardo. Okay, good. The screen sharing works.
Yeah, can you see my full screen now?
Yeah. Okay. Very good. So we have Eduardo Gonzalo from IFT who's going to talk about Swampland conjectures and particle physics. Please.
Thank you, Mariana, and thank the organizers for giving me the opportunity to talk in this very nice Dark World to Swampland conference. So you have been hearing about the Swampland for quite a while now. And as Luis said this morning, I believe that the Swampland program can provide a new hope for String Fino, a new avenue to bring about the new ideas about String Fino. And I believe that there are several papers already in the literature that prove this. And I would like my talk to try to convince you a little bit of this idea. And this is just some provocative image to catch your attention. Okay, so in this talk, I will discuss two conjectures. I will try to use two conjectures in order to arrive at the interesting phenomenology. The first one is the pair production with gravity conjecture, which we proposed earlier this year, and is a generalization of the with gravity conjecture. And I will be talking for the most part of this talk about this conjecture, but at the end I will also discuss a little bit about phenomenology from the anti-de Sitter distance conjecture. So I will start with this slide because I know some people in the audience are not string theorists, and this was already in Aaron's talk this morning. But let me just remind you that the Swampland is the set of apparently consistent low energy effective field theories, which when you try to couple them to quantum gravity in the ultraviolet, well, it turns out that you cannot. And our job here is to find criteria which we call Swampland conjectures to tell us where the boundaries of this Swampland lie. And it turns out that these Swampland conjectures are often either here or here. So in this upper corner, we have conjectures which are well established, are quite rigorous, and we have strong evidence for them. But in terms of phenomenology, they are not so interesting, or the phenomenology is not so useful. But on the other hand, we have some conjectures which we have less evidence for them, but they are pretty useful, and the phenomenology that we can obtain from them is quite rich. In this talk, I will start with the weak gravity and the distance conjecture. Well, I will use versions of them which take us to this side of the corner, because they are we have less evidence for them, but the phenomenology that we can obtain from them is quite interesting. So in the first conjecture that I will discuss is the pair production with gravity conjecture, and we want a conjecture that is just a small generalization of the weak gravity. So I have to review what the weak gravity conjecture is, and we have to search together for a statement of it so that we can understand the statement of the generalization of this conjecture. So the standard argument for the weak gravity conjecture is based on black hole discharge. So if external black holes were able to decay, then it would be possible to have a large number of them, and this can be seen to be in tension with holographic bounds and would make the theory afflicted with pathologies. So the standard law is that the external black holes need to be able to decay. So if we think, for example, of a theory with U1 to the n gauge symmetry, then an external black hole of charge Q and a mass with the same as the charge should be able to decay. So there has to be a multiparticle state with the same charge of any possible black hole and with less mass, so that the black hole can decay. So for only one U1, this is just that the mass is smaller than the charge, and this is why we call it the weak gravity conjecture, because we can think of this as the Newtonian force, and this Q is what appears in the Coulombian potential. So it is important to discuss the convex Hall condition here, because I will come back to this later on. Okay, so a graviton, we know that it gives rise to scalar fields and graviphotons and the dimensional reduction. So it is, in some sense, reasonable to expect that we can compare the strength of the scalar interactions with the strength of the gravitational interactions. So we want to formulate a generalized weak gravity conjecture in a sense, in a way that we can include scalar fields, which is valid at least in 4 dimensions. But the approach is going to be different. So instead of having a weak gravity conjecture particles, so the particles satisfying the conjecture exchanging massless particles, this is a way that this is some diagrams that help us compare the strength of a certain interaction with the gravitational interaction. Instead of that, we will consider diagrams where in the propagators we have massive particles. So for example, we can compare the rate to produce a heavy state starting with some massless mediators, in this case photons. These are the diagrams for scalar QED. And we compare the strength, the rate to produce this pair of particles with the rate to produce it starting from graviton. So this is just a different way to compare the strength of the gravity with other interactions. In this way, we obtain the complementary information of gravity as the weakest interaction, and perhaps, since we are talking about pair production, this can be actually related to black hole decay. So perhaps this is even more closely related to gravity conjecture. Okay, so we will see that in situations like the convex Hall condition, we say nothing more than the weak gravity conjecture. So their proposal reduces to that one. And there are also complementary approaches to include scalar weak gravity conjectures, or to arrive at conditions where we compare the strength of gravity with the force mediated by moduli, and this is what appears in the repulsive force conjecture. But in this conjecture, for example, we cannot compare directly attractive forces with gravity. So it is different what we are doing here. Okay. Okay, so let's give a precise statement of the weak gravity conjecture for multiple U1s, so that we can do our next one and see that they are saying the same thing. Okay, so in this plot, we have 2 U1s. We plot here the ratio of charge over m of particles and multiparticle states in the spectra. So in this picture, we consider that there are 3 fundamental particles with charges Q1, Q2, and Q3, and we consider multiparticle states. For example, this one has charge Q1 minus Q2, and the mass is the sum of the 2 particles. And what we see here in this plot is that all of the multiparticle states, they lie in this hexagon, which is the convex Hall generated by these vectors. And what is in this gray area is the black hole region, which is the region where all the black holes lie. And in this case of multiple U1s, this is just the region where black holes have no naked singularities. And what the weak gravity conjecture tells you is that along its rational direction, so for each black hole, for each possible charge, there has to be a multiparticle state to which the black hole can decay. So the convex hole, the place where all of the multiparticle state lie, it has to enclose this black hole region. Okay. So for every rational direction in the charge lattice, there has to be a superextremal multiparticle state. This is what the weak gravity conjecture tells you. And our generalization is to say the following. Okay. For any rational direction, so for any possible Q, and for every point in moduli space, there has to be a stable or metastable particle whose pair production by either gates or scalar mediators, so there are two versions of it, at threshold is larger than its graviton production rate. So we are evaluating the diagrams at a certain scale because we have massive propagators. So we decide that this has to be at threshold. And notice that the diagrams that we have are purely quantum relativistic. They do not reduce to a classical limit. We're talking about pair production here. So it's something different, something new. So for example, this is just an example for a simple U1 interaction, so a scalar QED. We compute the rates at the bound that we find is exactly this one. So exactly the same, it exactly matches the weak gravity conjecture. We're saying nothing new. So if we define a state to be superproduced when the rate to produce it via any other interaction is larger than from gravity, then the statement of the pair production is that for every rational direction in the charge lattice, there is a metastable particle which is superproduced. So this is just a definition that we can see that the statement is really close to the statement of the weak gravity conjecture. Okay, also, if this is just to finalize stating the conjecture, since we proposed it not so long ago, when you think about the weak gravity conjecture, we know that it doesn't behave well as it states under dimensional reduction, but some stronger version of it is needed, as the two more well-established proposals that we have stronger evidence for are the tower and the sublattice versions of it. And in the same way, we can state a pair production with gravity conjecture that behaves well under dimensional reduction, although this is something that is still under study. Okay, so we have seen that the pair production conjecture gives you the same thing as the weak gravity for U1 interactions. Now let's apply it to something new, a situation where we have scalar fields. And this is what it's really interesting for phenomenology, which is my goal here. So let's consider a theory where we have a heavy state whose mass is determined in terms of some massless fields, some moduli, and we consider the rate to produce this heavy state starting from moduli and compare it with the rate to produce the same state starting from gravitons. And we find that gravity will be weak enough if this bound is satisfied. This is for a single field, this is for more than one. Now, a similar equation was proposed by Palti in the paper about the scalar gravity conjecture, and it was based on an identity on n equals to supergravity. This is also based on an identity in n equals to supergravity, and in fact, n equals to BPS states saturate this inequality, so it doesn't seem an accident that we obtain this equation. If let's try to study a little bit what this equation tells us. If we study the extremal solution, so situations where this bound is an equality, and we plug in that the mass square is given by an exponential of certain function, we can always do this. We find that this reduces just to this equation. So if we have a solution with m squared, then 1 over m squared is also a solution. So we have some kind of duality built in all of the solutions of the equation. So it's nice that we get some stringy thing as duality starting from field theory. Okay, so yeah, in all of the examples that we study, we find this duality, and in the large field limit, the states saturating the equality, they behave as KK momenta or Wien states. We have tested in stringy setups these conjectures. For example, we tested it in type 2A calabial compactifications with the particles satisfying these being BPS particles coming from DP branes wrapping even cycles, and they have these dualities and they saturate our bound. So this was a nice check. But okay, how does this lead to phenomenology, because this test that we have done and the equation as it stands and as I have explained it, it gives you bounds for the many string excited states, but which are coupled with the mediators in the massless sector, but they are very massive. So what we would really like to do is to obtain constraints on massless or nearly massless scalars which have relevance in particle physics or cosmology. I mean, this would be our goal. This is what we would really be interested in. So we have two ideas in order to do this, which I will briefly explain. So the first one is to assume that the potential of the moduli, once they get a potential after Susy breaking, or for example, so we assume that this potential depends only, so it depends on the moduli, but only through the mass of the heavy states. So if the mass of the heavy states fulfills the per production with gravity conjecture, we have some bounds on it. And if the potential of the moduli depends only through the mass of the heavy states which they are coupled to, because via some loop or whatever, there are no mechanisms in order for this to happen. For example, if the potential depends in this way on the mass of the heavy state, then we can obtain bounds on the potential. In particular, if we plug this in our conjecture, we arrive at this equation, which for de Sitter and de Sitter minima is well, for de Sitter minima it's similar to the refined de Sitter conjecture. Another way to obtain phenomenology, which is more predictive, but that we have less evidence for it at the moment, is what we call the strong scalar with gravity conjecture, which is to assume that the moduli themselves, they acquire masses obeying the same constraint. So this is saying that the self-interaction of the moduli needs to be stronger than gravity. And if we do this, then we arrive at an equation like this one, which has very interesting phenomenology, which we studied in a paper last year. And interestingly, if the diagrammatic interpretation provided by the per production with gravity conjecture leads to a different factor here, which doesn't change very much the phenomenology, but this is still not clear which factor should be here. I will not go into more details about this at the moment. Let me just give you a summary of this part. So we have provided a first direct derivation of a scalar with gravity conjecture in the sense that we're directly comparing the strength of scalar interactions with the strength of gravitational ones. And it is a general principle that also includes the convex Hall condition, and that says nothing new when all of the examples we have about the weak gravity conjecture should in principle hold and apply in the same way. The saturating solutions of this proposed inequality display built-in duality symmetries, and this is actually related to the absolute value of the rates. If we remember the equation that I showed you before with where we substituted the exponential of some function f in the equality. Now the connection with other conjectures like the repulsive force conjecture or the weak gravity conjecture is something that is under study. It is not clear whether in some situations they give you the same results or when are they different. And it will also be interesting to think if the per production with gravity conjecture, as it has been stated, is also related to Black-Scholes discharge or not. It would be interesting also to all the computations, although the diagrams that I showed you before, we have computed the rates in Minkowski background, and it would be interesting to do it in different backgrounds. We have tested it in some string compactifications, but it would be interesting to test it in further string compactification. And also, it would be nice to include non-abelian gauge groups in the mix to see if something new comes up. Okay, so in the next part of my talk, as I announced at the beginning, I want to discuss very briefly some phenomenology which arises from the distance conjecture, in particular from the anti-de Sitter distance conjecture, which, as you know, is a generalization of the distance conjecture, which roughly tells you that if you start from an anti-de Sitter backward, then Minkowski or de Sitter vacua, they actually lie at an infinite distance, and the effective field theory cannot smoothly take you there, but some tower of states has to come down and break down your effective field theory. In particular, it tells you that this infinite tower of states with a mass scale m, when we take the limit where your cosmological constant goes to 0, then in Planck units, this tower comes down as a power law of lambda, where the exponent here, this parameter alpha, is a positive order 1 number, and in a strong version of the conjecture, it is actually expected to be 1/2 for supersymmetric anti-de Sitter vacua. So the question now is, how do we extract phenomenology from this conjecture? So to do this, we consider our beloved standard model compactified in a circle. So we study the vacua of this theory, which are 3-dimensional vacua. And we find that there are actually, well, was already known that there are anti-de Sitter 3-dimensional vacua. And the cosmological constant, we obtain it as the minimum of this potential, and it's negative, of course. So according to the conjecture, if in a certain direction of field space, for example, by varying the Yukawa couplings, which is what one of the things we will do in a minute, if in a certain direction of field space, this 3-dimensional cosmological constant goes to 0, then some tower of states should become massless, and it should become massless in this way. This is from an upcoming paper with my supervisor Luis Ibanez and Ingrid Venezuela from Harvard. Okay, so we consider the infrared low energy sector of the standard model, where we have gravity, we have cosmological constant, we have a Maxwell field, and we have the neutrinos. This is a slightly generalized version where we can have more than 1 photon and more than 3 neutrinos. It is not specified, and the masses of the neutrinos are not specified. In particular, we will see that we will try to obtain some bound on the mass of the neutrinos. So we compactify in a circle. So this is the simple answer that we use, and the effective action in 3 dimensions is given by this formula, where we are interested in the effective potential, which arises from a one-loop computation, and we have also this 3-level term coming from the dimensional reduction of the 4-dimensional cosmological constant. So in the first part, we will consider that the cosmological constant is the same as in the standard model, the same value, so it's non-zero. And when we compactify the standard model, this plot is it comes from the compactification of the standard model. So in particular, we have 3 neutrinos, and the mass difference between the neutrinos are fixed by experimental bounds, although the mass of the lightest neutrino is not fixed. So we plot it for different values of it. If the mass of the lightest neutrino is large enough compared with the 4D cosmological constant, then we find anti-de Sitter 3-dimensional minima. And if we move along the direction, for example, where the Yukawa coupling changes, then this mass becomes smaller. And as the mass of the lightest neutrino gets smaller, then the height of the potential becomes 0, and then it becomes positive. But this happens at a position where R0 is finite. So the only possible tower that can come up here is the Kaluza-Klein tower. So starting from the standard model, you can conclude that there is a violation of the anti-de Sitter's conjecture, because there isn't any tower here that can come down as in agreement with the conjecture. So you are smoothly going from anti-de Sitter vacua to Minkowski and then to de Sitter. But interestingly, this happens only for a certain range of values of the lightest neutrino mass. So for different values of the cosmological constant, there is an upper bound on the neutrino, on the mass of the lightest neutrino. This actually happens for neutrinos of 4 degrees of freedom. So these neutrinos must have a Dirac mass. And in particular, this plot is obtained for 3 neutrinos in normal hierarchy, which have, at least they have a Dirac mass. So in the sense that it has 4 degrees of freedom. And we find that if the mass of the neutrinos of the lightest neutrino is light enough, for example, than the scale set up by the experimental observed cosmological constant, then this doesn't occur. So the theory is safe from this problem. So this is the way in which we obtain a prediction about particle physics, in a sense.
You have 3 minutes.
Now, thank you. So my two last slides are about an interesting situation where we consider that the 4D cosmological constant is 0. And now, if this is the case, then we see that this is the plots that we obtain when we move along the direction of the Yukawa. So we are reducing the mass of the lightest neutrino, and we see that as the Yukawa goes to 0, or sorry, as the mass of the lightest neutrino goes to 0, then the height of the potential gets smaller, but it never reaches 0. So and as it gets smaller, the position, so the position of the minima becomes larger. So this is consistent with the anti-de Sitter distance conjecture if the Kaluza-Klein tower, because the Kaluza-Klein tower is coming down and is breaking down your effective field theory. Oh, I don't know why I cannot go to. Oh, sorry. Okay, so yeah, so with our parameterization, this is the formula for the Kaluza-Klein mass, and analytically, we have been able to find that the height of the potential, so the 3D cosmological constant, is given inversely as the radian to the 6th power with some constant here that depends on the bosonic degrees of freedom, which are massless. In the standard model, this is 4, the 2 degrees of freedom from the graviton, the 2 from the photon, and the number of fermions, which in the standard model is fixed. It's 3 neutrinos. If they have Dirac masses, then this is 12 because they have 12 degrees of freedom. And the difference, the mass difference between the neutrinos. This is the only thing that this depends. So by putting these two together, we find that this tower comes down as a power 1/3. And the constant, the prefactor here from the standard model is of order 10. It's 21 actually. So my last slide, the result for this part. When the cosmological, we studied the compactifications of the 4D standard model, and when the cosmological constant in 4 dimensions was different from 0, the mass of the lightest neutrino was bounded from above, and further consequences will be in our upcoming work. When the cosmological constant is exactly 0, we find consistency with the anti-de Sitter conjecture, but there's in the original paper, it was argued that alpha has to be larger than 1/2 for this anti-de Sitter minima, and this was suggested by a square version of the de Sitter conjecture. So according to, for our results, there will be some contradiction with the particular values of alpha. So it can, perhaps it is the case that this alpha can take any value when the minima is non-supersymmetric. This is all I wanted to say. Thank you very much.
Thank you. Questions for Eduardo?
Hi. Can I ask a question?
Yeah, please.
Hi. When you introduced the convex Hall condition, you said that the weak gravity conjecture can be satisfied by multi-particle states. But then when you introduce your pair production conjecture, you stress that these were stable or metastable. That sounds more like the lattice version of the weak gravity conjecture you have. Do you have any idea of constraints on the lifetime of these objects? How metastable do they have to be to satisfy? Because if something is just a very, very mild resonance, I don't know why I could call that a particle. Do you have any idea of constraints on that?
Well, it has to be, yes. For the first thing you said, it's completely true. In a sense, our conjecture is, it only makes sense when you go to the full version with the tower or the sublattice version of it. So that's completely correct. For the second thing you said, so we are making a perturbative computation. It's at 3 level, and we want this computation to make some sense. So the state has to be long-lived enough so that the perturbative computation makes sense. We cannot say I cannot say anything more about this except that for consistency, this has to be the case. But I cannot say anything more precise.
Thank you.
Other questions for Eduardo?
Yes, I have a question.
Can I ask a question? Hi,
yes.
This is I'm a particle physicist. So when you were showing the relation between the neutrino masses that are given in your theory, I got the impression that you really try to predict the, let's say, lightest neutrino mass. Is this understanding correct? And if so, imagine it's measured and it comes out a different value. Yes, this plot, there's a different value. What would this imply for your theory?
Well, we do not have an argument that we are predicting the exact mass of it. We are just saying that it has to be lighter than this. I think it would be too. I don't have a strong argument to tell you that it has to saturate this bound at this point. So if you detect it, if you don't detect it at that scale, I wouldn't say very much. I think.
And if it turns out to be slightly heavier?
If it's heavier than this, then it would have to say either that we have to make a better computation, like go to more loops. But in principle, I mean, it is very, very close to this scale. But if you find it in a significant amount, then it would have to say that either some assumption that we made is incorrect. For example, perhaps the compactification that we are considering doesn't make sense for some reason, but a circle compactification of the standard model, it's in principle something very standard, so it should work. So perhaps it would be telling you that one possibility is that the anti-de Sitter conjecture has to be changed in some way so that it doesn't apply in this situation, or perhaps you could also argue that a different tower of states is coming down from some hidden sector, but this would be difficult to argue because these scales have been studied, and searched for experimentally. But I guess there could be a way out of this, or perhaps with some very massless fermion, like an action. There would be some situations, but with the standard model as it is, and no other particles, this is the results. But if something experimental is different, but what is certain is that something interesting would come out of it. Either we learn something about the standard model, or make some other phenomenological prediction, or learn something about the anti-de Sitter distance conjecture, I would say.
Okay, thanks a lot.
More questions?
I have a question. Thanks for the really nice talk, by the way. The question is about the ADS distance conjecture. Does this assume that the cosmological constant stays constant as you vary the parameters of the theory, or
yes, yes.
It's hard to test the conjecture if you have supersymmetry breaking scale above the cosmological constant scale, because then, of course, there's always an ambiguity of how would that vary as you vary in parameter space, because, yeah, that's essentially the cosmological constant problem. So,
yeah, we are assuming that there is some compactification where we can freely change the mass of the lightest neutrino, changing the Yukawa coupling, but the 4D cosmological constant is unchanged, as you said. So this is an assumption that some compactification exists where we can change, for example, the fluxes, which are affecting the Yukawa coupling, but the 4D cosmological constant is unchanged. If the cosmological constant changes, and this is actually a good question, is something that we are studying in a paper, and something that we will be discussing, that if the 4D cosmological constant changes while the mass of the neutrino is changing, then this also can be avoided. So it is another way out of this.
And the contribution just from the neutrinos, like the one loop contribution from the neutrinos, is that big in itself, or just from the change in the neutrino mass?
Sorry, what? Can you repeat that question?
Yeah, I don't know. I mean, I think if it just the change in the neutrino mass, is it possible to calculate how that contributes to the cosmological constant in one loop?
We didn't compute that, but like if you parametrically assume that the 4D cosmological constant depends in some way, you can see that this thing gets avoided. But we didn't make the full computation of how it would depend.
Yeah. Okay. All right.
We just you assume some dependence.
All right. Thank you.
Thank you.
Any other question for Eduardo?
Hello. You showed some robustness and usefulness figure of the conjectures. And at which point do you place your new conjectures?
So the pair production weak gravity conjecture is a generalization of the weak gravity conjecture and would be in this side of the plot, because it's the evidence we have for it is less stronger than from the weak gravity conjecture itself, but the phenomenology is quite useful. And the anti-de Sitter conjecture is a close brother of the distance conjecture. So it has, I would say, a strong evidence, but it is also very useful. So it would be also on this side of the plot. This plot is due by Oguri, by the way.
I see. So in this sphere, BSM, is it a consequence of the non-SUSY ADS conjecture, or is it another conjecture?
No, it's another conjecture. It doesn't follow. So the pair production conjecture does not follow from the non-supersymmetric ADS conjecture. It is a different ramification. A different ramification. I'm sorry that was implied by the plot. I didn't mean that.
So, what is BSM?
This plot is an old one. Is because from starting from the non-supersymmetric ADS conjecture, you also find that the three-dimensional anti-de Sitter vacua of the standard model are dangerous, and they disagree with this conjecture. So you can also obtain bounds and prediction for beyond the standard model starting from this conjecture. It's actually the very similar computation, but this is from a different conjecture.
I see.
I'm sorry if you got confused. It was my fault.
And did you also consider the inverted hierarchy case?
Yes. I mean, I didn't show you the plot in this talk, but it would be something similar. But the precise bounds are different. But it will probably appear in a paper soon. So.
Thank you.
Thank you.
Any more questions? Okay, if not, let's thank Eduardo again and all the speakers of this morning, afternoon, evening, whatever the time it is for you. Thank you. And I believe we have an unleaded discussion now. The organizers maybe want to step up.
Yes, I guess so. So I guess we will leave this Zoom session open for the next 30 minutes or so that people can casually discuss informally, maybe, without a chairperson. So
it's an open mic or what?
Maybe I can ask something to Joe if he's there. Joe Conlon.
Hello, Mariana. Yeah.
Yeah. No, to Joe Conlon, are you there?
I'm here. Can you not hear me?
Sorry. Okay. No, this value of the anomalous dimension of 8 point something, does it, I mean, from the CFT, is there anything particular about this value?
No, I mean, other than that it's very specific. So if you happen to, from some other direction, happen to come across a 3D CFT with this value of like 3/2 on 1 + square root 19.
But
yeah.
So there's no, I mean, I guess it would be very weird to find a CFT with this particular lightest, no? Or I don't know. Then what is your feeling about the CFT dual?
I mean, I think like constructing some microscopic version would be very hard. I mean, so generally, as I think CFTs which have this sort of explicit CFT. I don't think explicit CFTs which have this structure where they look like they are dual to these sort of classical supergravity theories, where you've got only a small number of single trace low dimension operators. Is a very hard thing. But yeah. I mean, in principle, you can work with the ADS side to make statements about what the CFT would be like if it were to exist.
So
is that what?
You say? I mean, well, other than that, it needs to have this field with an anomalous dimension.
I think it's more the thing of saying that if you have that, because in principle the ADS side defines the CFT, and if it was some way to kind of if you could pick up on something that appeared like inconsistent about the CFT, then that can tell you that there'd be something inconsistent about about the ADS thing, and then and then you're actually talking directly to the Swampland.
Right.
So there are some results for CFTs about signs of anomalous dimensions, but they tend to apply for double trace things of identical operators rather than the sort of the mixed ones I was talking about.
Yeah, I see. And for the large volume scenario, there's always this extra light fiber moduli, right? I thought, I mean, in order to get the ADS minimum, don't you have always these extra light moduli?
Yeah, you always have the volume one.
Right, but also another one.
You always have the volume one and the axion, and it's dual axion.
Right, so but I thought it worked. I mean, you need to have this Swiss cheese structure.
Yeah, but that doesn't require a fiber structure. That just you've got the overall volume one, and then the holes in the cheese are like the blow up modes. But those modes are heavy.
Okay.
Yeah.
I see.
Yeah, because those modes are much heavier. I mean, the one that you always have to have is the volume, but.
I see.
Yeah.
I see. So these extra light moduli are not. I mean, they could be there, but.
Yeah, I mean, I was talking about the fiber thing. That would be. Yeah, they could be there. They could not be there.
Yeah, I see.
Yeah.
Okay, thank you.
Yeah.
Okay, this is supposed to be a moderated discussion, so I'm not the moderator.
I have a question for Eran.
Hi, Liz.
Hi. Concerning how you call it, this story of the having trivial kinetic terms in the ultraviolet, and they are generated in loops. Up to now, this has been done only for kinetic terms of bosons and vectors, and then now you do it with fermions, but what about the rest of the couplings? How the rest of the couplings of the effective theory are generated? Not only kinetic terms. I mean, the effective theory has.
Yeah, I mean, from the example. Sorry?
Gauge vertices and things, Yucabas.
Yeah, so I mean, for me, a guiding example is something like the CPN model. In the CPN model, there's it's a theory in the UV of scalar field. It has interactions. It has a gauge symmetry, U1 gauge symmetry, but the gauge field has no kinetic terms. And then when you flow to the IR, you generate a kinetic term at one loop. So in that case, the couplings will not be generated through the flow. I mean, of course, they will flow. RG couplings will flow, but in that case, I mean, when people say that gauge fields should be emergent, I think that's a natural expectation in quantum gravity. That means that the kinetic terms are generated. And I think couplings need not be. I mean, there are also theories of like, you know, Adler has a theory, what he calls emergent gravity, where Stephen Adler, this is from a long time ago, where you start from, you have a theory with a metric. So it's not that you don't have that quantity in the theory, but you just generate the kinetic term for that quantity in the IR. He does it through RG flow, actually. So I don't have I don't know what the theory is at the species scale or in the UV. The toy model of the CPN, there are models, solvable models, where you have emergent gauge field. In that case, the interactions are there in the UV. They are there in the UV. They are just the kinetic terms are generated in the IR. Yeah, so I mean, there's also kinetic terms are also a bit special because, you know, in the Lagrangian, they're the only things which explicitly involve space-time coordinates. And, you know, my feeling was always, it doesn't really make sense to write down a kinetic term at the species scale, because the species scale is a strong coupling scale of gravity. And when gravity is strongly coupled, there's probably no notion of space-time. So it doesn't really, I don't really know how one would even write something like a kinetic term at a strong coupling scale of gravity. But interactions should be fine. I mean, yeah. So, I mean, interactions don't involve explicitly space-time coordinates, but kinetic terms do. So, yeah.
It's like having a topological field theory in the UV, right? That you have the couplings. Like if you have a BF theory, you have the coupling, but you don't have the kinetic terms. And then
that's what
you can start.
I see words. I don't see. I don't see the meat of those statements. Really.
Which statement? Sorry.
I mean, if you get rid of the kinetic terms, typically you obtain some topological field theory that can be trivial or not, depending whether you keep some interactions or not.
Well, you have auxiliary fields which do not propagate.
When you're talking about kinetic terms here, you mean anything with a derivative, like also interactions?
Yeah, I think so. Yeah. If you just have high derivative ones, you typically end up with ghosts in the theory. So yeah, I don't know. I mean, you can, if you don't like this kind of thinking, you can forget about it, because at the end it doesn't really matter. I mean, it's the same thing as saying you reach strong coupling. If the kinetic terms are, you know, if the coupling is of order 1, or if there is no coupling at all, there is no propagating gauge field. So if you think of a kinetic term for a gauge field, you know, if it's not a big difference in the RG, in the UV boundary value, if you take G to be of order 1 at a species scale, or you just say there's no kinetic term at all. At the end, in the IR, you get the same result. So that's why, you know, people like the US people, and they call this kind of emergence, but they really mean unification. They just say that everything flows to strong coupling at the same scale. And that's all you need to get these results. That's the computation is the same. What happens at that scale where things become strongly coupled, that can be an abstract philosophical discussion that you may or may not be interested in. But the IR, the correlation in the IR between the tower states and the gauge coupling, That's just a statement that you float a strong coupling at the species scale for any field in your theory. That you don't need to worry about what happens at that scale. If you're interested, we postulate that in fact, there is no dynamical field at that scale, but it doesn't make any difference. Is that clear? Or, I mean, like in the one loop running, you have 1 over g squared in the IR is 1 over g squared in the UV plus the one loop piece. Now, if you're weak coupling, 1 over g squared in the IR is a very big quantity. Okay, and then 1 over g squared in the UV, it doesn't matter if it's 0 or 1. I mean, if it was a truly emergent gauge field, like in a CPN model, it's just 0, exactly 0. And that's just telling you there is no 1 over g squared f squared term in the action. But it doesn't matter if it's 0 or 1, because you're balancing an equation with something very big on the left-hand side. That's got to balance against the one loop term, which must be very big. The order 1 UV contribution can be 1 or 0, it doesn't matter. So something important to say is that this relation, this explanation of the weak gravity conjecture in terms of this emergence proposal doesn't rely on having no propagating fields at the species scale. It just relies on having the field flow to strong coupling at that scale. That's the only thing that goes into it. So if you don't like the idea of emergence and no propagating fields, you can just say that all this shows is unification. All fields should become strongly coupled at the same scale. That's what the weak gravity conjecture seems to say. Of course, that makes complete sense from a unified theory perspective. You would expect everything to get unified. Yeah.
Mm-hmm.
No. Hello?
Hello.
I don't know what happened. I mean, you all disappear. But okay, maybe this is a signal. Maybe this is a good point for ending things today, and we can resume tomorrow. So thanks to everyone for attending, and well, we keep on seeing each other the rest of the week.
Okay, very good, very good.
Bye to everyone.
Bye-bye.
Bye.
Hi, everyone.
Bye bye.